Welcome back, guys. So this is question 2.1 of our book Electric Circuit by Nilsson. So from today we have been starting the exercise questions of this book. So let us first start by question 2.1. So the statement of this question is the interconnection of ideal sources in the circuit in figure 2.1 valid or not? Explain. Okay, so the first thing here is that whether these connections are valid or not. So these are all the independent sources. This is the independent voltage source, this is one, is also this one is the independent current source. Okay, so what is here and what should I consider for the validity of this? So the circuit will not be valid if it is like this one, the two voltage sources are connected, two or more voltage sources are connected in parallel in such a way that it has some voltage 15 volts and it has some voltage 16 volts or 20 volts. Somehow voltages are different in between both of them. Okay, so that these two connected are in parallel, and we know that in parallel the voltages will remain the same. So therefore this one is incorrect and it is not valid electric circuit. Okay, similarly another type of circuit is that if the two or more current sources are connected in series are not similar. Okay, so suppose this is the 5 amperes and this one is 10 amperes or somewhat different than this 5 amperes. So in this branch, in this series branch, we know that always the current remains the same. So therefore these type of circuits are also incorrect as well and are not valid circuits. Okay, so these two type of circuits if are not available, or if you can see any other combination just like these one, so you should keep in your mind that these connections are invalid. Okay, so looking at this circuit, there is nothing like this one. This is the voltage source, this is the voltage source, both of them are connected in series with each other, which is invalid. It doesn't satisfy this one, it doesn't satisfy this one, and this is a valid combination. Similarly, this current source is connected in series with these two voltage sources, and similarly this is the only current source here. So therefore the current through only this branch is 5 ampere. Okay, so therefore this one is the valid electric circuit. Okay, so that is the explanation for part A. Okay, so let me remove it. In part B of my question, identify which sources are developing power and which sources are absorbing power. Okay, so to discuss that which are these sources which absorb and which develop the current, let us first consider this current which is flowing in the clockwise direction. So here in considering this one, we can see that this is the current and here this current flows from positive to negative. Okay, so this one is leaving out from this terminal, and as this is the conventional or ideal circuit, so therefore we are considering the conventional current. So therefore when it will enter through positive and will come out of this negative terminal, so therefore this will be the absorbing source. Okay, so therefore let me write here V20 20 volts. This is what? This is the absorbing source. Okay, similarly here you can see that here the current is entering through negative and coming out of this positive. So therefore this is what? This is the developing power source. So therefore here we have V15 and that is the 15 volt source which is the delivering or developing power source. Okay, similarly here we can see that this is the current which is coming out of this one. So this is positive, this is negative for the current source. You should also keep in your mind that this should be the polarity here if nothing is given. So here again current is entering through this negative and coming out of this positive. So therefore this I 5 amperes is the 5 ampere and this is also the developing or delivering source. Okay, all of them are the sources. So these three are explained here. part C of it is verify that the total power developed in the circuits equal the total power absorbed. Okay, so let me solve it, and this is part C. So first let me find out all the absorbed power. Okay, so the only absorbed power is through this one, which is P20. Okay, so here this would be I20 multiplied by V20. Okay, which is what this V is the voltage across it, and I20 is the current which is flowing through all of this circuit. And we should keep in our mind that this is the series circuit, so therefore I20 is equal to the I15, which is equal to 5 amperes as given here in this branch. Okay, so the current through all of this is same, so therefore the I20 is 5. Okay, and the V20, which is already given here, is that is 20 volts, so therefore it is 100 watts. Okay, similarly the other one is the developed power. So let me write here about the developed power. So what is the developed power? So the total developed power is the power which is developed by this 15 volt source plus this 5 ampere source. Okay, so therefore the power developed by this 15 volt source is I15 multiplied by the V15 plus the power developed by this current source is I5 multiplied by the V5. Okay, so do we know this value? Yes, this is already known, and also from this formula as well. Do we know this value? Yes, this is already known from it as well, and that is 5 amperes. Okay, this is the I5. Do we know this value? Yes, V15 is known, and that is the 15 volts. But do we know this value? No, we don't know this one. So therefore, in order to find it out here, let me find it out here. Applying KVL through this loop, we will see that if this is the current, we will see that this is the 20 volts. Okay, minus 20 volts, and if this is the positive, so this is 15, and also this one is what the power through across it is V5, so this is equal to 0 according to the Kirchhoff's voltage law. Okay, so V5 here would be what? It would be the 5 volts as from this one. Okay, so let me write these values here as we have found it out. So let me write these values. This is 5 multiplied by 15 plus how much is this? This is 5 multiplied by 5. Okay, so it would be 75 plus 25, which is 5 multiplied by 5, so this one is 100 watt as well. Okay, so this one is equal to this one, so therefore both the power developed and the power absorbed are the similar ones. Okay, so this is what this is from part A to part C, and for part D I will solve it in our upcoming video. Till then, take care of yourself, and if you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So today we are going to solve part D of our question, and previously we have solved part A, B, C of question 2.1. so the part D of it is repeat A to C, reversing the polarity of the 20 volt source. Okay, so this is the 20 volt source, and reversing it we will get what? Let me reverse it. This is the first source, this is the second source, okay, and the third source is here we have. Okay, the polarity of it remains the same. This is of 5 amperes, its polarity will remain the same. This is plus minus how much? that is 15 volts, and we have to reverse the polarity of this 20 volts. So this will remain the 20 volt, but the polarity of it would become this plus, this minus, while here we can see that it was negative and positive here. Okay, so now we have this circuit. Let us analyze it. First of all, is it the valid circuit? Okay, so this is a valid circuit because of the reasons we have described in our previous lecture, that there is none of the voltage source connected in parallel with the other voltage source, and also only a single current source which is in this loop. So therefore the value of current is known in this loop, and that is 5 amperes. Okay, but we don't know the value of voltage across it. The part B is identify which sources are developing power and which sources are absorbing power. Okay, so let me have this current. Okay, so this is the current, and we can see that here it is moving from negative and coming out of this positive. So therefore this V20, this 20 volt is now what? This is the developing source. Okay, similarly here this is coming in from this negative and coming out of this positive. So therefore this V15 is also what? This one is the 15 volts, and this is what? This is also the developing one. In order to find it out, we don't know about this voltage, so let me have it. This is V5. We don't know about its polarity, so let me find it out by this one. So in this loop, applying the KVL, okay, applying KVL here, we know that V20 plus V15, because the polarity of both of them is now same, so therefore we are writing them, and plus V5. Suppose the polarity of it is unknown, so this is 0. So V5 is what? This is minus V20 plus V15. Okay, or writing the values of them, it would be 20 plus 15. So this V5 is how much? This is minus 35 volt. Okay, so minus 35 volts means the polarity of it is opposite of these polarities. So therefore writing them here, it will be what? It will be positive here and negative here. Okay, so therefore as the current here moving from positive and coming out of this negative, so therefore this V5, which is the I5 source, okay, and that is the 5 amperes, this is what? This is the absorbing source. Okay, so this is what? This is the absorbing, while the two ones here are the developing ones. The part C of it is verify that the total power developed in the circuit equals the total power absorbed. So the power developed here is the power which is developed by these two, and power which is absorbed by this source. Okay, so these are basically the developed power, and here this is the absorbing. So let me first find out the developed power. Okay, so the developed power, which is PD, that is the summation of the power by 20 volts and the 15 volts. Okay, this V20 is VI, so V20 and I20 plus V15 plus I15, and here it is understood that in this series circuit I20 is equal to the I15, and that is equal to I5 as well, and that is 5 amperes. Okay, you have to keep it in your mind. So let me put them here, the values. So this is 20 multiplied by this 5 plus V15 is 15 multiplied by 5, so it would be 100 plus 75, so it is 175 watt. Okay, so this is what? this is the power developed. Okay, now in order to find the absorbed power, let me find it out here. So absorbed power is the power which is absorbed by this 5 ampere source. So this is P5 and this is V5 multiplied by I5. So V5 is known, that was 35, as I'm just writing the magnitude of it, and I5 is how much? That is 5. Okay, so it would be, that is 175 watt as well. Okay, so we can see that here the developed power and the absorbed power are equivalent. So therefore we have solved part A to C for part D as well. Okay, so that's it for today, in which we have seen the validity of the circuit and solve it for different quantities ranging from voltage, current, and then to the powers as well. Okay, so that's it for today, and I will see you with some more interesting stuff in our upcoming video. See you soon. Welcome back, guys. So today we are going to solve two questions which are related to the validity of the electric circuits. So these are question 2.2 and 2.3, and both of them are basically relevant with each other. So let me first go through question 2.2. So the statement of this question is, if the interconnection in figure 2.2, okay, so this is the figure 2.2, is valid, find the total power developed in the circuit. If the interconnection is not valid, explain it. Okay, so here this is the circuit, and we can see that there is no reason to make it invalid. Okay, I have previously told you that a circuit will be invalid if two or more than two voltage sources are connected in parallel, which has the voltage values different from each other. So it means that the different parallel voltages are connected, which is inconsistent with the rules of the electric circuit. Okay, similarly, if you have a single loop and two or more than two current sources are connected in it in such a way that all of them has the different values, so that is also the invalid circuit. But there is no connection like that one which we can call the invalid, so this circuit is the valid electric circuit. Okay, so if this is the valid electric circuit, we have to find what? We have to find the total power developed. In order to find the total power developed, we have to see that what are the sources which are developing the power. So here we have this 50 volt source, 10 volt source, 40 volt source, and 5 ampere current source. All of them are basically the independent sources. Okay, so first of all, in order to find it out, let me find out the voltage across this. So let me call it V5. We don't know its polarity, so first of all let me apply KVL here in this circuit. In order to apply the KVL, let me consider the direction of the current. So let me consider the direction of the current, and let me take it this one which is inconsistent with this current source. So if we have taken it, so let me use this voltage source here as well. So this is what, let me call it V40. Okay, V40, and here we can see that current is entering through negative and coming out of this source through this positive terminal. So I am taking it positive. Here we can see that current is entering through this positive terminal and coming out of this negative terminal. So therefore I am taking it negative. So minus V10 here again. So this is the anti-clockwise current. So this is entering through this positive, coming out of this negative. So I am taking it negative as well. So this is V50. Okay, so the last one here is 5. So I am taking it as it is because this one is the unknown. Okay, so this must be equal to 0. So all of these values are known except this V5. So in order to find this V5, we have here minus V40 minus V10 minus V50. Okay, so here we have, so let me put these values. So this is 40. Okay, this is negative 40 minus 10 minus 50. Okay, so this is what, this is 20 volts, positive 20 volts. So what is mean by this positive 20 volts? Positive 20 volts means that the polarity we have taken for this V5 is correct, and the polarity we have taken for this one was of similar as this V40, because both of them are the positive ones. So therefore this is now here negative and this one is positive. Okay, so this is the polarity of it. Now in order to see which are the developing and which are the absorbing sources, here according to this current, this source, because here the current is entering through negative and coming out of this positive, let me use this color, current is entering through this negative coming out of this positive, here again current is entering through this negative coming out of this positive according to this current direction. So these are this V5 and this V40, both of them are the developing sources. So in order to find the value of it, so PD is equal to what? PD is equal to the power developed across this 5 ampere source plus the power developed across this 40 volt source. Okay, so let me have the formula, and we know that P is equal to IV. Okay, here I is I5, okay, which is the current going through this source, and here this is V5. Similarly here we have I40 and V40 as well. In this series circuit we can clearly see that the current through all of these elements is the similar one, and that is the 5 ampere. So let me write here 5 multiplied by the value of V5, which I have already found out is this 20. Okay, and the value of I40 is again the similar one, which is this one, a constant overall through this branch. So this one is 5 multiplied by V40, this is 40. So let me find it out. This is 100 plus this is 200. Okay, so this is now 300 watts, which is the developed power through this circuit. Okay, so that is what, that is the solution of the question, because we are asked to find out the developed power and we have found out by this formula. Okay, so that is the solution of question 2.2. so now here in this question 2.3, let me solve it. So in solving this one, we can see that one current source is this one, and while the other current source is this one. So first of all we have to see that whether this is a valid circuit or not. These two voltage sources are connected here, which is completely valid. These two, one current source, one voltage source, these are connected in parallel, which is also valid because no two or more than two different voltage sources are connected in parallel. So this is a valid circuit, and also there are no two or more than two current sources which are different in values are connected in series. So here we can see that this is a valid source. After it we have to find what? We have to find this V10 and V5 as well to find out the power developed by this source and this source as well. So this V10, we can see that this is in parallel with this 100 volt source, so the polarity of it will be the similar one as that of this one, and the voltage across this one will be the similar one as that of this source. Okay, in order to find out the voltage across this V5, let me consider the current here. So this is the current here, and let me use the KVL here. So in order to find the KVL here, we have to do what? Here this will be, let me consider this one as the positive, so it will be negative positive. So let me consider this one as V5. Okay, this is now current is entering through positive coming out of this negative, so this is minus 40. Okay, and also as the current is entering through this positive coming out of this negative, so this one is minus 100 as well, and this is equal to 0. So in order to find this out, it is minus 140 equal to 0, and the value for V5, once we will find it out, this is 140 volts, and this is now known. Okay, so now in order to find the power developed by this 10 amps, this is what? This is, let me have P10, and this is the I multiplied by V10. So I10 is known, that is 10 amperes. V10 is also known and we have already found it out, that is 100, which is 1000 watts. Okay, and the value of the power which this source 5 amp source is developing, let me call it P5. This is also I5 multiplied by V5. Do we know the value of I5? Because this is the current source, so that is already known. 5 amperes multiplied by V5, and that is 140. Okay, so here finding it out, what will we get? It will be 700 watts. Okay, so the total power developed here is PT is P10 plus P5. Okay, adding them together we will get 1700 watts, and that is the solution of our question. Okay, so that's it for today, in which we have seen the solution of question 2.3 and also the solution of question 2.2 as well. Okay, so these are the two solutions. If you have any question regarding these solutions, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.4 from the similar book of electric circuit by Nilsson, and the statement of this question is, if the interconnection in figure P2.4, this is the figure, is valid, find the total power developed by the voltage sources. Okay, here we have this voltage source and this voltage source as well. If the interconnection is not valid, explain why. Okay, so first of all, let me explain here that what is mean by the valid and invalid electric circuit. So in terms of the voltage sources, if we have a voltage source connected here, some other thing just like resistor or capacitor or some other element here, and another voltage source is here, and also one or two or many voltage sources are here which are also connected in parallel with them. So suppose this is VA, the value of it is VB. Okay, and there are many, and let me have here VC. Okay, plus minus plus minus plus minus. Okay, such that VA is not equal to VB. Okay, so in this case, if you have two or more than two sources here such that the voltages they have are different from each other, so this one is basically the invalid circuit. Why? Because of the reason that in parallel circuit voltage always remains the same. Okay, here the voltages will remain the same if this is point A, B, C, D. Okay, if these are connected in parallel, and what is meant by parallel? Parallel means that both the terminals of the elements are connected in similar point. Okay, if I want to redraw it, I can redraw it in this way as well. Okay, and if there are more than these sources, these are here. Okay, so here we can see that the connection points A and B here are similar, so these are in parallel with each other. So when these are in parallel, the voltages remain same in between them, but if these are not similar one, this source or this circuit is basically the invalid circuit. Another case is that if we have a series circuit, and in this series circuit I have two or more than two current sources. Okay, so let me have here, and these current sources are not equivalent in values. If this is IA, this is IB. Okay, and if IA is not equal to IB, this one is also the invalid circuit, because here according to the circuit analysis rules, the current in a branch of a series circuit will always remains the same. Okay, but here we can see that this is not the phenomena when this condition is satisfied. Okay, so keeping these two things in our mind, let us evaluate this circuit. And here we can see that if we have this loop and this loop as well, and we want to see that what are the conditions, whether this or this is met or not. So we can see that according to this first circuit, we can see here that none of the voltage sources are in parallel with each other. These two nodes are not connected directly with these two nodes, so therefore these are not in parallel with each other. Similarly, if we see here in this loop, the current remains the same, which is this 8 ampere. But here when we come to this loop, we can see that here this current is the only constant one, but in this branch the value of it is 4 ampere, while here this is 3 ampere, while this IA is constant throughout this loop. Therefore we can see that here in this loop there are two current sources, and 4A is not equal to 3A. So therefore this circuit is just like this one, and we can see that this is invalid circuit. Okay, so I have explained the reason that why is it not a valid circuit, and I hope you have understood the reason behind the invalidity of this circuit. So that's it for today. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. This is question 2.6, and the statement of this question is: consider the interconnection shown in figure P2.6. This is the series circuit which contains two independent sources. One of them is the independent current source, the other one is the independent voltage source, while this one is the current source which is dependent upon this V1. Okay, you can see that here this diamond shape source diagram, which basically shows that this is the dependent source, and this arrow sign shows that this is the current source. So therefore this one is the dependent current source, and the value of it basically describes that it is dependent upon this V1. What are the dependent current sources? These can be the transistors or many other devices which depends upon some other sources. We will go through it in our upcoming videos. So let us move to our question now. So in this circuit, what value of V1 is required to make this a valid interconnection? And B is, for this value of V1, find the power associated with the voltage source. Okay, so in this series circuit, we can see that this is a series circuit, and here we can see that here this current remains the same to make this and this equivalent. If this 400 milliamperes is flowing through this circuit, these two current sources should have the similar value. Means in this branch, as this one is the single branch in this circuit and this is a series circuit, and I have told you in our previous videos that to make a circuit valid, we must have all the current sources connected in a single branch should have a similar value. So therefore the value of it and this one, these should be the similar ones. So therefore 400 milliamps should be equal to what? It should be equal to V1 divided by 50, which are these two ones. Okay, so in order to make them equivalent, it is what? This is 0.4 actually, and this is V1 divided by 50. So the value of V1 should be equal to what? It should be 0 multiplied by 0.4. So this is what? This will be 20 volts. Okay, so this should be the value of V1 if we want to make this one a valid circuit. If the value of V1 is 20 volt, this will be a valid circuit. Okay, so that is what? That is basically the solution of part A of our question, where we have found the value of V1 for the validity of a circuit. In part B of our question, if we have found the value of V1, which is 20 volt, what should be the power associated with the voltage source? As we can see that the actual direction of the current is here, for which we have also found out the value of V as well. If this is the direction of the current, which is basically the actual direction, then the current enters through this positive one and comes out of this negative terminal. Okay, so what does it shows? It shows that this source is basically the absorbing source. Okay, so when this one is the absorbing source, V1 is the power absorbing source, not the developing source. These two are the developing sources. So the power associated with this one is the well-known power formula is P is equal to IV. So the current through this one is the similar one which is flowing in this circuit, and that is given by this one, that is 400 milliamps or 0.4 amperes. Okay. Similarly, the V of it is also known, and that is 20, which is the voltage across it. So let me find it out. Finding it out, this will be 2. So this is 8 watt absorbing power. Okay, so that's it for today, in which we have discussed the dependent current source and also what are the requirements for making any circuit a valid electric circuit. So that's it for today, and I will see you with some more interesting stuff in our upcoming video. See you soon. Welcome back, guys. This is question 2.7. And the statement of this question is, consider the interconnection shown in figure P2.7, where this is the figure. Here, let us first discuss this figure. This is a voltage source, or we can call it the independent voltage source. Similarly, this one is the current source, and this is called the independent current source because of this circular shapes. Okay, this is a circular shape, this one is also a circular shape, and the arrow here basically denotes the current source. Similarly, here this diamond shape basically represents the dependent source, and here the terminals of negative and positive shows that this is a voltage source. So therefore this one is the dependent voltage source. So over what it does depend, it depends upon this I delta. So therefore this one is the current controlled dependent voltage source, and this I delta is here. Okay, so this current basically controls this one, so it depends upon this current. So what are the examples? It exists in the real world. Yes, there are many examples, and one of those examples is the operation amplifier, which is the current controlled voltage source. Also bipolar junction transistors or many other transistors are basically the examples of these one. Okay, so there are many other dependent sources as well, and we will talk about them in our upcoming video when we will solve the questions related to them. So let us go through the statement of this question. So in this circuit, what are the different parts? So in part A, what value of alpha is required to make this a valid interconnection? So what is alpha? Alpha is the multiplicative term here with this I delta, and in order to find it out, we can see that in this circuit, if these two are basically the common nodes in between this voltage source and this one, so to make this a valid circuit, in the parallel ones, the voltage across here should remain the same. Voltage here in between these terminals and these nodes should remain the same. So therefore let me solve it, and in solving it, minus alpha I delta should be equal to 6. Why minus? Because you can see that here this is positive negative, and here this is negative positive. We cannot change the terminals of it, but the dependency of it can be changed, and it can be changed by putting the negative with this one. Okay, do we know the value of I delta? Let us look at it here, and in this branch, let me use this color. In this branch, we can very clearly see that this is I delta, and in this branch the current is constant, which is 15 milliamps, and we can see that the direction of this 15 milliamps is in opposite one as that of this I delta. So therefore the value of I delta is what? That is also minus 15 milliamps or minus 0.015 amps. If you know this value, let me put it here, and putting it here, it will be minus alpha minus 0.015 is equal to 6, or alpha is equal to this minus is plus 0.015 equal to 6, or alpha is equal to 6 divided by 0.015. Okay, solving it, what will we get? This will be 400. Okay, so the value of alpha to make this circuit a valid one should be kept at 400, otherwise this will be an invalid circuit. Okay, so this is the solution of part A. In part B, for this value fell for, find the power associated with the current source. So this is the current source, and to find the power across it, we know the formula, that is P is equal to IV. Do we know the value of voltage? Yes, that is already known, and this is the similar voltage which is here. So if we have here VA, so it can be like this one, this one, and this one. This is the current source, this is the voltage source, while this one, sorry for my drawing here, this one is for this dependent voltage source. We can see that all of these three are basically in parallel with each other, having these two nodes common in between them. So these are basically parallel, so voltage will remain same across them. So therefore the voltage across it will be 6 volt as well. Okay, so the value of voltage is 6 and the current is 15 milliamps or 0.015, which is known by this branch current. So 0.015 multiplied by what, multiplied by 6. So let me find it out. 15 multiplied by 6 divided by what, divided by 1000. So this will be what, 90 divided by 1000. This will cancel out and it will be 0.09 watt. Okay, so this is what, this is for the power across it, or it can also be the 90 milliwatts. Okay, so this is the power across it. In part C, is the current source supplying or absorbing power? Okay, we don't know about that, whether this current source is supplying or absorbing the current. So in order to find it out, let me find out the polarity across it. So the constant polarity across it is due to this constant source, which is the independent source. So therefore this polarity will remain same here, and it will be plus minus here because of this polarity. This can be changed by choosing the negative value of alpha or I delta. So it is not constant, it is the dependent source. So the polarity of it will solidly depend upon this constant source. So therefore it will be plus minus. And also we can see that the actual current here basically enters, let me use this color, enters through this positive one and coming out of this negative terminal. So it shows the absorbing ability of this one. So therefore this current source is basically the absorbing source here. Okay, so it absorbs the power here. So that's it for today, in which we have solved question 2.7 of our book. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.8 and 2.9. Today we are going to solve both of them, as both of them are closely relevant with each other. So let us go through question 2.8 first. So according to the statement of this question, is the interconnection in figure P2.8 valid or not? Explain. Okay, so this is P2.8 and we have to see that whether this is valid or not. And B is, can you find the total energy developed in this circuit? Okay, so this is the second part of it. So first of all, let us see that whether this one is valid or not. So this is the common point here. Here this is the voltage source, the current source, this one is the source as well, and these are the two sources here. So we can see that here the voltage is VA, which can be drawn just like here as well. Okay, this one is the dependent source, this is here, this is here, and we have it here. Okay, so this is the current source, the voltage source, the current source here as well, and the voltage source, and this is the current source, and this one is the dependent upon this I1, and therefore this one is the current dependent current source. Okay, so this is the dependent current source which depends upon this current. We can see that here these all are connected in parallel, and these are not the constant sources, and these can adjust their voltages according to the current flowing through them. Okay, so therefore in order to see that what are the voltages across them, so let me have here VA, let me have here VB, and let me have here VC. So if the circuit is valid, it means that VC is equal to what? VA with this 20 volts, and it is equal to VB with this 30 volt. Okay, but why did I not write this 30 volts and this 20 volt? Because we don't know the polarities of this VA and VB. So therefore in order to do so, let me have first current. Okay, so this is the supposed current and this is the second current here. Both of the currents should be equal in direction. If this one is in the clockwise direction, the other one should also be in the clockwise direction. Okay, so we can see here that this is negative, this is positive, and as the direction of this current and this current, these two are in opposite with each other, so therefore one current is flowing through it like this one, and the other one from the other one, the actual direction is this one. So therefore the polarities of both of them will be opposite than each other. So therefore the polarity across this one will be what? It will be negative and positive, because this is positive negative, it will be negative positive. Okay, so therefore applying here the concept, and we want here the positive and here the negative because of these signs. So therefore this one will be the positive one while this one will be the negative one. So this one minus this one, if you apply the KVL through this one, so it will be VA minus 20 volts. Okay, so this is through this branch. Similarly in this branch we can see that what is the voltage here? This is the current which we have supposed, and here it will go through this positive, come out of this one. Similarly the actual direction of current is also this one. Okay, so therefore the polarities of both of them will remain the same, because this should remain the positive, this should be negative because of this polarity, and here it will be what? It will be plus minus, because here it is also plus minus. So therefore applying KVL across this branch, what will we get? These two voltages will add with each other, so VB plus 30 volts. Okay, so here this shows that this one is the valid circuit. Okay, so this is the validity of circuit. Can you explain the total? Can you find the total energy developed in the circuit? Explain. So in order to find the total energy in this circuit, we must have the currents which are known. Okay, so this is the current, but the voltage across this source, the voltage across this source and this current, these are unknown. In order to find them out, we have to solve this equation, which can have many solutions as well. Okay, if we don't know the values of these voltages, it is not possible for us to find the total energies developed here. Okay, so that is the solution of the question which we were solving, and this was 2.8. Similarly in question 2.9, the statement of this question is, if the interconnection in figure P2.9 is valid, find the total power developed in the circuit. If the interconnection is not valid, explain why. So first of all we have to see that whether this interconnection is valid or not. So therefore this one is what? These three are this one and this one. You can see, let me draw it here as well. So this is here, this one is here. Okay, so this is plus minus 40 volts, this is the current source here, this is the dependent source. Okay, and this one is the current dependent voltage source because of these polarities, current dependent voltage source, and this is the independent voltage source here as well. This is the 60 volts, and another voltage source which is connected here within these two branches here as well. So this is 30 volts. Okay, so the voltage must remain same between all of them, because if this is VA, so VA is 30 volts, because here across these two nodes the voltage is 30 volts. Okay, similarly here in order to see that this is 1800 Ix, so 1800 Ix is here, and what is the value of Ix? As it is flowing through this branch, so therefore the value of Ix is 50 milliamps. Okay, or that is 0.05 amps. Okay, putting it here, okay, what will we get? The voltage across it, let me have it here. So the voltage across it, let me call it VA. So the value of VA would be 1800 multiplied by 50 multiplied by 10 to the power minus 3, because of this Ix which is here. So finding it out, it will be what? It will be 180 multiplied by 50 divided by 1000. So these two will cancel out here. 18.5 is 90 divided by 10, so this will be 9. So the voltage here is 9. So applying the KVL across this branch, let me use this one. So in this branch, if we apply the KVL, it will be what? It will be VA plus 60. The value of VA is known, that is 9 plus 60, which is 69, which is showing that the voltage VA here is what? This is 69 volts, which is in contrast different than the actual voltage which is here. Okay, so therefore the two different voltages are connected in parallel with each other, which is impossible. Okay, which is impossible for the validity of a circuit. So that's why this circuit is invalid circuit. So that's it for today, in which we have discussed two very complicated circuits and saw that how to find the polarities of different sources if the polarities are unknown, and also the validity of the circuits as well. Also we have seen the current dependent current source as it is given here, and the current dependent voltage source which is here as well. So that's it for today. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. This is question 2.10, and the statement of this question is find the total power developed in the circuit in figure P2.10 if V naught is equal to 5 volts. So this is figure P2.10, and here the value of V naught is given, that is here, and the value across it is 5 volts. Okay, so that is what? That is the voltage which will be here, here and here as well, because if we see, all of these are basically the common ones, so therefore these are in parallel. Okay, so these three branches, this one, and this one, all of these are in parallel with each other, so therefore the voltage will remain same across them. So here, in order to find the values of the power developed across everyone, we have the formula, that is P is equal to IV, means I should know the value of the current which is flowing through that source and the voltage which has been developed across that source. Okay, so here we have different sources. Here this is the voltage source, the value of the voltage is known, while the current value which is in this branch only, that is known, and that is 9 volts. Okay, similarly here in this source, which is the current source, the value of current is known, while the value of the voltage is unknown. So let me call it here plus minus VB, and we have to find it out. Okay, here in this branch the value of the current is again known, and that is 6 ampere because of the availability of this current source, while the value across it is unknown. Okay, we have to find it out, and that is V of A. So what do we have to find out? Let me write it here. We had to find out V of B here. VB, VA is also unknown, which is here, and the value of VG, which is unknown because the value of current is known, while the value of VG is unknown, and also the value of V naught, that is already known. Okay, so let us first find out the values of VB, VA and VG. In order to find the value of VB, what do we have to do? We have to apply the KVL here in this branch. Okay, so we know the total voltage here, and that is 5 volts. Okay, in order to find out the value of the unknown voltage here, we have to apply here the KVL, Kirchhoff's voltage law. So here it will be what? It will be, let me write it here, it will be what? It will be VB plus 20, that is equal to 5. Okay, so in order to find it out, we will get here VB is equal to, this will be there, so it will be minus 15 volts. So therefore the answer of this VB is minus 15 volts. Okay, so that is known now. In order to find the value of this VA, which is here, we know that here in this source the value of V naught is equal to 10 VA. So V naught is equal to 10 VA. Okay, and the value of V naught is known, that is 5. This is 10 VA, sorry, this is VA, so that is VA, and from it we can very easily find the value of VA, that is 5 divided by 10, or that is 0.5 volts. Okay, so the value of this VA is also known, and that is 0.5 volts. Now to find out the value of this VG, again let me use the KVL here as well, and in this branch the KVL here would be what? Here this all is known, and that is 5 volts. Okay, because of around this branch which is here, and let me write these voltages. So VA is this positive, negative, so let me take it positive 1. Okay, and let me write this VG, that is minus VG. Okay, so let me write their values. So 5 is equal to VA, the value of VA is known, and that is 0.5 minus VG. To find the value of VG, we have here 0.5 minus 5, so it will be, the value of VG would be minus 4.5 volts. So therefore this is minus 4.5 volts. Okay, so these quantities are now known, we have found them out, and now we can very easily find out all the values or all the powers across them as well. Okay, let me now clean it. So now let us start it from this source, which is here 9 amperes. Okay, so let us start it from this one. Let me use this color here. So this is P9, and in order to find the value of the power here, the formula is this one, the value of current through it, which is 9, known, and the value of voltage, which is VB, so that is minus 15. Okay, so P is equal to IV here, so 9 multiplied by minus 15 is minus 35 watts. Okay, and this negative denotes what? It means that this current source basically develops the power of 135 watts. Similarly, this 20 volt source, so here the current through it is known, and that is 9, and the voltage across it is 20. So this is now what? This is 180 watts, and the sign associated with this one is positive. It means that this one is the absorbing source. Okay, now let us move here, and this 6 amperes, P6 is what? The current through is 6 multiplied by the voltage across it is 0.5, so this is 0.5, and that is 3 watts, and plus sign denotes that this is the absorbing source. Okay, now this VG, let me call it PG, and the current through it is known, that is 6. Okay, and the voltage across it is minus 4.5, which is already known. Okay, one thing you have to keep it in your mind here, that if this one is minus 4.5 and the value here is 0.5, okay, so if we apply here the KVL, we will see that the value of it here would become what? It will be minus 4. Okay, which is not possible because of this 5 volts. So in order to maintain it, because this will have to maintain the voltage of 5 volts here, it will, the actual value of the current will be in the opposite direction as that of here, so therefore it should be the negative one. So here the current here, the opposite one as that of here, so it will be what? It will be the 27 watt, and this positive sign denotes the absorbing nature of this source. Okay, so now all of these are known. In order to find the power associated with this source, what do we have to do? We know the value across it, that is 5 volts. We don't know the value of the current which is passing through it. So let me have here this current, let me call it I naught. It reaches this node and splits into two parts. Let me call it IA, or let me call it IB, and here IA. Okay, so according to the KCL here, I naught is equal to IA plus IB, let me put their value. So the value of IA is 6, the value of IB is 9, so this is 15 amperes. Okay, so in order to find cross it, let me call it P naught. So P naught will be equal to 15, which is I multiplied with the voltage, which is 5 here. So it will be what? It will be the 75 watts. Okay, but here keep it in your mind that as this is the dependent source, so therefore the actual direction of the current should be inwards, not outwards. So therefore the current, if this is inward, so it will be minus 15, so it will be minus 75 watts, which is the developing power. Okay, so this is one method. Another method is that in this overall circuit, the value of the developed and the absorbed power should be equivalent. Therefore here let me use this color here, P9 plus P20 plus P6 plus PG and plus this P naught, this should be equal to 0. All of these values are known except this P naught. So let me put them here, minus 135 plus 180 plus this P6 is 3 plus 27 plus P naught, that is equal to 0. Or here adding them all together, we will see that it will be 75 plus P naught equal to 0, which will ultimately give me P naught equal to minus 75 watts, which also shows the developing nature of this dependent source. Okay, so this is the developed power and this one is the developed power as well. If we add them together, the total power developed PD, and that would be P naught plus P9, so this will be minus 210 watts. Okay, because this P naught is minus 75 watts, this P9 is minus 135, so adding them together we will get minus 210, and that is basically the solution of the question which is asked. So that's it for today. If you have any question in your mind, please ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.11 of section 2.3, and the statement of this question is for the circuit shown in figure P2.11. So this is P2.11 and this is the figure where we have this independent current source, this resistor, and this is the polarity of the voltage here. Okay, so what do we have to do? In part A of it, we have to find V. Okay, so let us first find V from it. So this is part A, and to find out V, we know the Ohm's law. So according to it, V is equal to I into R. Okay, so here in order to find the V, we need to find out the value of I and R. So the value of R, which is the only resistor here, so all the voltage will be consumed across it. So the value of R is known, the value of I is given by this current source. So therefore let me write it. So 15 multiplied by 10 raised to power minus 3 for 15 milliamps multiplied by R, so that is 3 multiplied by 10 raised to power 3 because of this kilo. Okay, so these two will cancel out and ultimately we will get 45 volts. Okay, so this is the value of V in part A. Okay, so after it we have to find the power absorbed by the resistors. This is part B. In order to find the power absorbed by the resistor, we have to use the formula, which is P is equal to I square into R. Okay, or there is another formula as well, and that is V square divided by R. Similarly, for the sources, as we have done in our previous questions, for the sources, the value of the P or the power is always I multiplied by V, which is the current through that source and the voltage provided by that source. Okay, so this is for the sources, while these are for the resistors. Okay, for the impedances we will discuss them in our upcoming videos. Till now let us concentrate over the resistors, as we have a resistor here. Okay, so you can take any of these formulas and it will give you the similar output. So let me take this formula, v square divided by r. So p of r is v square divided by r. So the voltage across it is known, and that is 45, as we have already found it out. 45 square divided by r, and r is 3 kilo ohm or 3000. Okay, so let me find it out. 45 square, this is 2025 divided by 3000, so that is 0.675. okay, so that is the answer, or we can also write it in terms of the milliwatt. So it would be 675 milliwatt. Okay, that is the solution of part B. In part C, it is given that reverse the direction of the current source and repeat part A and part B. So here this is the current source and we have to reverse it. Let me reverse it here. Okay, so let me redraw it. So this is the source, this is the resistor. Okay, and the polarity should remain the same. This is V, this is 3 kilo ohm, while it is given that we have to change the direction of this current. So this is 15 milliamps. Okay, so therefore the value of current is now what? That is minus 15 milliamps because of this value. Okay, so by changing these values, all the previous values will be negative, as we will write here the value of I equal to minus, so it will become here V equal to minus 45 volts. Okay, what does it mean? It means that the polarity we have selected is this one, but the actual polarity which is given by this negative sign is opposite as that we have supposed here. Okay, so this is positive, but the actual polarity here is what? The actual polarity is plus minus, and that has been due to this opposite direction of the current source. Okay, so that is for this part of question. In part B, which we have to do again, let me use the similar, as the values of the voltages are now here. So negative minus 45 square will be the similar one, and this is, and the value of power will remain the same because of the value here, and the value of power will remain 675 milliwatt. Okay, the value of the power will remain the same. So that's it for today, in which we have seen a very basic circuit and analyze it by using the Ohm's law and the formula for the power for the resistors. Okay, and for the sources as well. Okay, so if you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. This is question 2.13, and the statement of this question is: a pair of automotive hand lamps is connected to a 12-volt battery via the arrangement shown in figure P 2.13. So this is the figure P 2.13, and here we can see this arrangement. In the figure, the triangular symbol is used to indicate that the terminal is connected directly to the metal frame of the car. Okay, so these are basically the triangular symbols. Okay, which basically denotes that these terminals or these nodes are connected to the metal frame of the car. So the part A of it is construct a circuit model using resistors and an independent voltage source, and B is identify the correspondence between the ideal circuit element and the symbol component that it represents. Okay, so this is basically a circuit, and here in order to draw it, let me first draw it as it is. So this is what, this is the battery here, this is plus, this is minus, as we have here. This battery is now connected with this switch. Okay, so let me represent this switch as this one is the switch. Okay, this is the switch. Then these this is basically a node which is connected with this lamp A and lamp B as well, which means that both of these are in parallel. So therefore this switch will be here, and here we will have here this lamp A, and here at this point we have this lamp B. Okay, so let me represent it A with B, and this is the 12-volt source. Let me, this one is S, which is for switch, and these are all the bulbs here. Okay, so these are basically what? These are basically symbols which denotes that these terminals are connected with the metal frame of the car. Okay, so these are basically connected in the similar points, so therefore we can also connect them as it is here. Okay, so this is the circuit diagram, but in real world all of these elements, the cables, the switch, the battery, the lamps, all of them has the internal resistance. So therefore in order to connect them here with the real world sources and having in consideration the internal resistances of the cables and the battery as well, let me redraw it here as well. Okay, so if the internal resistance, this is the battery, okay, and let me have the internal resistance of this battery represented with R of B. So this is the internal resistance of this battery, this is plus minus. Okay, this is a switch, and switch has also the internal resistance as well, so let me represent it with R of S as well. Okay, similarly this battery is connected with this switch, so therefore this part of cable has also the resistance. Let me represent it with this RBS, so this is also the resistance RBS here as well. Okay, so these are the resistances, and then we have this switch. Okay, this is the switch, let me represent it with this S. After this switch is connected with this lamp A and lamp B with this part of the cable, and let me represent its resistance with RA. Okay, so this is another resistance, let me represent it with RA. Okay, then there is this lamp which has also the internal resistance. Let me represent it with what? Let me represent it with this RAA. Okay, and then this lamp here. Okay, I'm considering now it. Okay, similarly here from this to this there is also this cable here as well, and the resistance of it, let me call it what? Let me call it RBB. Okay, and then this lamp which is here as well. Okay, so these are all the resistances which are in accordance with all the cables and the elements here. Also, when these are connected with the metal frame of the car, the metal frame also has some resistance, so let me represent it with this resistance, because this is RM1. Okay, this is the metal resistance, and also this one is also connected with the metal resistance as well, and let me represent it with this RM2. Okay, so these are connected here as well. Okay, so this is what? This is basically the actual diagram which shows us that this is the real world diagram, while this one is composed of these sources which are the ideal sources. This is the 12-volt source. Okay, this is the switch, this is lamp A, this is lamp B, and all the resistances here, this one, this one, this one, this one, this one, and all these ones. Okay, these are basically what? These are the resistances which basically shows us the connection between the ideal circuit elements and the resistances in accordance with all of them which are in the circuit. Okay, so that's it for today. If you have any question, if you have any ambiguity regarding the understanding of this question, you can ask me in the comment box. See you soon. Welcome back, guys. I hope all of you will be fine. So this is question 2.14 of the electric circuits by Nilsson, and the statement of this question is the terminal voltage and terminal currents were measured on the device shown in figure 2.14 as given here. Okay, so this is the figure 2.14. The value of V and I are given in the table of figure P2.14b. So this is a table for each of the current and amperes. The applied voltage V in kV is also given here. Okay, so you can see that in all of these type of circuits, this one is the independent variable, while this one, the current, is the dependent variable. Okay, use the values in the table to construct a circuit model for the device consisting of a single resistor from appendix H. Okay, so this is basically a circuit. This voltage has been applied. This is the device, and if we can draw it precisely, it is this resistor. Okay, the value of current is applied by applying the value of voltage, which is here. Okay, so this is the voltage. When applied, the current flows here. Okay, so in this table we can see that when the values of the voltage is applied, the current also is measured, and from it we can see that the graph of it will be like this, and it will be the ramp shape. Okay, and the slope of it will remain the same, which is the inverse of the resistor. Okay, from it we can very clearly see that according to the Ohm's law, V is equal to IR. Okay, and also the value of R here is V by I. Okay, let me put all these values here. So putting each one of this row here, we can see that V is minus 7.2 into 10 to the power 3 divided by minus 6. This is equal to minus 3.6 into 10 to the power 3 divided by minus 3. Okay, this is also equal to the 3.6 into 10 to the power 3 divided by 3. This is the current for this one, and 7.2. Why am I writing this 10 to the power 3? Because of this kilovolt. Okay, divided by 6, and this is also equal to the 10.8 into 10 to the power 3 divided by 9. Okay, pick any one of them and you will see the answer of it. Let me take this one, and it is what? It is 3.6 into 10 to the power 3 divided by 3, which is also 3600 divided by 3. Okay, which is what? Which is basically 1200 ohm or 1.2 kilo ohm. Okay, so that is what? That is basically the solution of this question, where the value of this resistor is 1.2 kilo ohm. Okay, so that's it for today, in which we have seen the solution of question 2.14. In our upcoming video, we will try to solve the questions which are relevant with this question, and we will try to solve the similar question in a single video. Till then, take care of yourself, and I will see you in our upcoming video. See you soon. Welcome back, guys. This is question 2.15, and the statement of this question is a variety of voltage source values were applied to the device shown in figure P2.15a. So this is the figure where this is the voltage source, this is the current, and device is connected with it in series. The power absorbed by the device for each of the voltage is recorded in table given in figure 2.15b. This is the table where the applied voltage is here, and the power absorbed by this device is listed here as well. Use the values in the table to construct a circuit model for the device consisting of a single resistor from appendix H. So as it is known that this is a resistor, so here for the resistor, the value of power absorbed by the resistor can be written in terms of the voltage is V squared divided by R. Okay, the only term here constant is this R. So therefore, from this formula we can write the value of R is equal to V square divided by P. Okay, so all of these values, when for each of the pair here, this is pair 1 2 3 4 5 6, each of the row here will give us the constant value, and that constant value will be what, let me write it here. So that would be the R, and here it would be P V square divided by P. So V square minus 8 whole square divided by 640 into 10 as power minus 3 for the first couple here. For the second one, it would be minus 4 whole square divided by 160 into 10 as power minus 3. Why minus 3? Because this is in milliwatts. Okay, also for this one, it would be 4 square divided by 160 into 10 as power minus 3. For the fifth one, it would be the 8 square divided by the 640 into 10 as power minus 3, which is also equal to this 12 square divided by 1440 into 10 as power minus 3, and so on. Okay, the last one here will also be here, and that would be 16 square divided by 2560 into 10 power minus 3. So now picking any one of these values, we can find out the value of the resistor. So let me pick this one because it seems easier. So to find out the value of the resistor from it, 4 is 16 divided by the 160 multiplied by 10 power minus 3. It would be, this 16 is 10 times this, and it would be 1 over 10 to the power minus 2. Okay, or this is also 10 to the power 2 or 100 ohm. Okay, so that is the value of this resistor which is here, and this circuit can also be drawn like this one. This is the circuit, this is the voltage, and the resistor here is 100 ohm. Okay, so this is the solution of question 2.15. Let me proceed to question 2.16 because that is also the relevant one, and that is here. Okay, so in this question, a variety of current source values were applied to the device shown in figure P2.16a. Okay, this is the circuit in which the voltage source is now replaced with this current source. The power absorbed by the device for each value of the current is recorded in the table which is here. The current is applied and the power absorbed by this device is here. Use the values in the table to construct a circuit model for the device consisting of a single resistor. Again, this is a single resistor, and this device can also be drawn like this one, as we had previously seen, but this one is the current source. Okay, and the current source basically develops this voltage. Okay, this is the resistor as it is given, and we want to find out the value of this resistor. Okay, to find it out, again we know the power formula for the resistor, and that is in terms of the voltage, which we previously seen was V square divided by R, while for the current, that is P equal to I square R. Okay, so that is the value for it. In order to find the value of R from it, this formula, so it will be P divided by I square. Okay, so that is the formula in which the only thing here in this table which will remain constant will be this R. So let me formulate it for this one. So here this R is equal to what, P divided by I square. So P is for the first pair, here is for this pair, it would be 8.25 divided by 0.5, that is equal to 33.00 divided by 1.0 for the second one. Okay, for the third one, that is that is also the squarish. Okay, so this is also square. Also for the others, it will be 74.25 divided by 1.5 square. Okay, and so on for the others one as well. Okay, for this we have to put it in this formula. Okay, so let us take any one of them. So let me take this one because it seems easier because of this denominator term, which is 1. So from it we can very easily see that the value of resistor is what, that is 33 ohm. Okay, and that is what, that is the value of this resistor, which is 33 ohm. You also need to keep in your mind that these denominator terms are the squarish ones. So therefore the 10 to the power minus 3, this is 10 to the power minus 3 will be here, and also in the squarish terms it will be 10 to the power minus 3, and then it will be whole square. Okay, you need to keep in your mind all of these. You have to multiply the 10 to the power minus 3 and then squarish term, because these cannot be cancelled out. One 10 to the power minus 3 will be cancelled out while the other one remain the same. So therefore the answer here we would get will not be 33, but it will be, let me solve it here. Most of the people make this mistake, so therefore I have first gone through it and now I am solving it like it is. So it will be 33 into 10 to the power minus 3 divided by the 1 into 10 to the power minus 6 because of this squarish term. So it will be what, it will be 33 divided by the 10 to the power minus 3, which is 33 into 10 to the power 3, and ultimately we will get 33 kilo ohm. Okay, so you need to keep in your mind that this is not 33 ohm. Okay, let me do it. It is not 33 ohm, while this one is the 33 kilo ohm because of the terms here. Okay, you need to keep them here because most of the people, and I have seen it in many question papers, answer sheets, in many quizzes, that people cancel them out, and the remaining term here, which is the denominator, is in the squarish form, so they forget to put them here. Okay, so that's why I have solved it here separately. So that's it for today. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.17. So this is the figure P2.17, and from this figure we have to find what the part A of it is. Find V naught using Kirchhoff laws and Ohm's law, and B is test the solution for V naught by verifying that the total power supplied equals the total power absorbed. Okay, so in our previous video we have seen the use of the Kirchhoff laws, the Ohm's law, and today we are going to implement it here in this circuit. Okay, so first of all let me see that what is here. So you can see that the current which is here, this is, let me call it I naught. When it reaches this junction which is here, it splits into two direction. The first one, let me call it I2, and this one is I1. Okay, so applying here KCL, so according to the KCL, the first equation here is I naught is equal to I1 plus I2. Okay, so this is the KCL here. Similarly here in this branch only we can apply the Ohm's law, and here V naught is equal to what, that is I1 into R, and the value of R is 5 kilo ohm, so this is 5 kilo. Okay, let me call it equation 1 and this equation 2. Okay, the third one here is, let me consider this overall branch. Okay, this branch, let me identify it by using this overall branch. Okay, and here applying the what, applying the KVL, if we call the voltage drop across this one as plus minus V2K. Okay, and the voltage here is, let me call here, this is V naught, okay, because this is given, and this is V2K. So applying the KVL here, what will we get? V naught is equal to the voltage drop across this one, which is V2K. Okay, and here you can see that this is as that of the same polarity as here we have this V naught, because here if you see this is here, this is minus plus 5 volts, this is V2K and V0. Okay, so the V0 here is positive, means that it is connected to this positive terminal while this is the negative terminal. Or we can also represent it like what? It can also be represented like plus minus, which has the same polarity as that of this one. So therefore here from this one it will be subtracted because it is of the same polarity as that of V0, so it will be minus 5 because of this 5 volts. Okay, in a single equation it is obtained from a single equation where we had V0 plus 5 minus V2K. Okay, that is equal to 0, and that is the KVL. From this equation ultimately the equation we got is here, this one. Okay, so let me call it equation 3. So now we have three equations, 1, 2 and 3. Okay, so in this equation the value of V2K is what? We can see that here this is I2, and I2 is moving through this resistor and giving us what? Then it is giving us the voltage. So therefore the value of V2K is I2 multiplied by 2K. Okay, so the value of V0 here, let me solve it. The value of V0 here is what? That is I2 multiplied by 2K minus 5. Okay, similarly the value of V0, as we have seen, that has also the value which is here. So comparing this equation, let me call it equation 4 and 2, what will we get? Comparing them both, because the left sides of both of them are equal, so here we will get this. This is 5K, so 5K means 5000. So 5000 multiplied by I1, that is equal to, this is 2K means 2000. So 2000 multiplied by I2 minus 5. Okay, or ultimately we can also get it like moving this to the other side, 5000 I1 minus 2000 I2, that is equal to minus 5. Let me call it equation 5, and that is equation we have. Okay, so now we, which are here, the first equation is here, the second equation is here. Okay, so here in these two equations let us compare them, and comparing them we have to put the value of I0 here as well, and using the similar color here as well. So the value of I0 is 20 milliamperes, so that is 20 into 10 to the power minus 3, that is equal to I1 plus I2, and let me call it equation 6. So now we have here this equation and equation 6, and we can find the values of I1 and I2 from those equations as well. Okay, so let us move down somehow. Okay, so as we have this equation, so let me multiply 2000 with this equation 6. What will I get here? On the right side we will get 2000 I1 plus 2000 I2, that is equal to, multiplying it here at this side, what will we get? This is 10 to the power minus 3, so it will be cancelled out and we will get here 2 only, so ultimately we will get 40. Okay, again we have this equation, so let me write this equation here as well. So let me write it here. So it will be 5000 I1 minus 2000 to minus 5. So let me add both of these equations. So adding them together, these two will cancel out, and here we will get 7000 I1, that is equal to 35. From it the value of I1 will be 35 divided by what? Divided by 7000, so it will be this 2, so 1 over 200 amps. Okay, so this is what? This is the value of I1, which is the current here. So now in order to find the value of V0, we have this equation number 2. Let me use this equation number 2. So the value of V naught will be equal to the value of I1, which is 1 over 200 multiplied by 5000. Okay, these two will cancel out and ultimately it will be here with this one. So the answer of it is 25 volts, which is the value of V naught, and that is the solution of part A of our question. And in this part we have seen that how to find out the value of V naught using the Kirchhoff's laws and Ohm's law. In the part B of it, test the solution for V naught by verifying that the total power supplied equals the total power absorbed. So what are the powers which are supplied? So here we can see that this is positive, this is negative, here this is negative, this is positive, so therefore the polarity opposite of it, so we will put the negative side with it, and we will write here V multiplied by I for finding the power here. Similarly, you can see that here this is negative, this is positive, while the polarity here again is positive, negative. So therefore, as this one is also the source, so it will be minus V into I. The value of I is known, which is I2. We will find them out, and then from both of these two we can find out the value by P equal to I square R. The values of I are known and the values of R are also known. Here the value of I is I2, here the value of I is I1, both of them are known. You can find them easily. If you don't know, from this formula, you know the I1, you know the I0, you can easily find out the value of I2 as well. Okay, today we have seen that how to find out the V naught and also how to find out the total power, because here once you will find the total power developed and total power absorbed, you will see that both of them are equivalent. So if you will have any ambiguity or any difficulty in solving the question like this one, or you have any difficulty in solving part B, please let me know. I will solve it again. So that's it for today. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. I hope all of you will be fine. So this is question 2.17, and the statement of this question is: consider the circuit shown in figure P2.17. This is a figure. In this figure, part A of it is find V naught using Kirchhoff's laws and Ohm's law. B, test the solution for V naught by verifying that the total power supplied equals the total power absorbed. Okay, so this is the circuit, and here we have to apply the Kirchhoff laws and Ohm's law. So first of all, let us see that what is meant by Ohm's law, what is meant by the Kirchhoff's law. Okay, so let me use this green color for it. So for Ohm's law, we know that according to the Ohm's law, V is directly proportional to I. Okay, in a linear circuit, when you will increase the value of the voltage, which is the independent variable, the value of the current will also increase. Okay, so removing this proportionality sign, it will be V equal to IR, where this R is the constant, and if the resistance is constant, increasing the value of V will also increase the value of I as well. Okay, so this is Ohm's law. Also, by discussing the Kirchhoff's law, we have two laws, two very famous laws. The first one is the KVL or Kirchhoff's voltage law. The other one is the KCL, Kirchhoff's current law. Okay, so what is this? According to the KVL, the sum of all the voltage in a loop, in a branch, will also be equal to 0. Okay, or we can also interpret it like that: in a branch, the sum of all the voltage rises will be equal to the all voltage drops. Okay, so suppose we have here this branch. This is what? This is the resistor, this is another resistor, here we have this resistor. Okay, so if there is no voltage here, this is, let me call R1, R2, this is R3. Okay, and if we apply here the voltage source, this is V of S, this is plus, this is minus, so it will be VR1, VR2, and it will be VR3. Okay, so as these are the resistors, which are the passive elements, and it always absorbs the energy, and voltage is dropped across them. So therefore it will be plus minus here, plus minus here, plus minus here. So according to the KVL here, the value of Vs will be equal to Vr plus Vr2 plus Vr3, or ultimately we can also write it like Vs minus Vr1 minus Vr2 minus Vr3. This must be equal to 0. Okay, so this is in the what? This is in this circuit. Suppose here if we have a branch, okay, if we have a branch like this one, many people confuses here because of it, and this is what? This is the ground one. Okay, so here we have, let me have here Vp. This is the, let me call it 1 kilo ohm resistor, and here we have this one negative positive 5 volt. Okay, so we can also apply it here the KVL as well. And what will be the KVL? As this one is a positive terminal, so it can be interpreted like that this is positive and the other terminal here will be negative. Okay, so applying here, what we will get if we consider the direction of the current like this one, so we can see that the current is entering through this negative, coming out of this positive, so it will be Vp. Also this is the voltage dissipating device, so plus minus, so here it will be V1K. okay, this is the voltage across it, and here again you can see that the current is entering through negative, coming out of this positive, so this is again the V5 is again the voltage drop. Okay, so and this one is what? This one is the ground one, and it is always on 0 volts. So here let me use it 0 volt, and it will be equal to 0. Okay, we can always apply it to branches, to loops, to meshes, and anywhere where do you want. Okay, so this is the KVL. Also in KCL, if you want to interpret that what is KCL, so KCL says that to a node, if this is a node, if the current is moving towards it, let me call it I naught, so it will be equal to the currents which are going away from this node. Okay, so this is I1 and this is I2. Okay, so according to KCL, Kirchhoff's current law, the current moving towards a node in a circuit will always be equal to the sum of all the currents moving away from a node in a circuit. Okay, so here we can see that I naught is equal to the I1 plus I2. Okay, so here we can see that this one is here. So whatever the direction of currents here would be, we have to utilize them here as well. If the currents are moving away, so the sign of them will be positive. If these are coming towards it, it means that these are coming towards them. So therefore if all the currents are coming towards them, let me have this one, this current is coming towards it, this is also, let me take it IB, and this is IC. So here it will be I naught plus IB plus IC. This will be equal to 0 because all the currents are moving towards this node, and that's why the summation of all the currents will be equal to 0. Okay, so that is basically the interpretation of the Ohm's law, Kirchhoff's law, KVL, KCL, and all the things which we will be using in this question. Okay, so that's it for today. We have seen that what is mean by Ohm's law, what is mean by the KVL, KCL, and in our next video we will try to apply them in question 2.17. Till then, take care of yourself, and I will see you soon. Welcome back, guys. This is question 2.18, and the statement of it is, given this circuit shown in figure P2.18, find A, the value of IA, the value of IB, the value of V0, the power dissipated in each resistor, and the power delivered by the 50 volt source. So this is the circuit diagram. Here we have this source which is of 50 volts. 4 ohm resistor is connected in series with it, while 2 resistor 20 ohm and 80 ohm, you can see that these are connected in parallel with each other. How to see that whether these are in parallel or not? If the two legs here, you can see that the 2 points or the 2 junctions here are common in between them, and we can also draw them here as well. Okay, it is like this one. Okay, this is the source and these are the 2 common points. We can see that here this and these 2 legs of these 2 resistors, okay, these are connected here. So that's why these 2 are in parallel with each other, and these 2 are also in parallel with this source, which is of 50 volts and 4 ohm as well. Okay, so these 3 are in parallel with each other. And what is the voltage here? This is given, this is V0 here, so therefore this V0 voltage is also here as well. Okay, so what are the currents? Let me show the currents here as well. This is IB, this is IA. Okay, and let me represent here this I0, which is the current supplied. Okay, so we can very clearly see here that this V0 is equal to the voltage across 80 ohm, across 20 ohm, and the voltage which is generated by this 50 volts minus the voltage which is subtracted by this 5 ohm. So let me call this voltage, the polarity of it will be plus minus. Why? Because this is the voltage dissipating device, and the current here is I0, and the voltage, let me call it V4. Okay, so this is the overall data we have. Now on the basis of it, what will be the points which we should know here is that the first law, and we are going to practice all those laws here. The first law is Ohm's law. Okay, so where will we apply here the Ohm's law? Here the value of V0 is equal to what? That is the current through this resistor 80 ohm and the value of this 80 ohm. So this is what? This is IB, which is this current. Okay, this is IB multiplied by this 80 ohm. Okay, why? Because V is equal to IR is the law according to Ohm's law. Similarly, this voltage, if we see that these 2 are in parallel, this is a similar voltage which is across this 2 ohm as well. So we can also write it the 20 ohm resistor multiplied by the current through it, and that is IB. This is also V0. Okay, if we want to see that what will be the voltage here, we can see that this is again V0 here as well. Okay, and that is what we have here. The second law here we are going to apply is the Kirchhoff's voltage law. Okay, so what is KVL? Let me look at this loop. Okay, when we are going to take a look at this loop, we can see that here this is, let me have this current which is I0. It is now entering through this negative terminal, coming out of this positive terminal. So this is the voltage rise. Here it is entering through this positive, coming out of this negative. This is voltage drop, and this 20 ohm resistor, and we know the voltage drop across it, and that is V0. Okay, so if we want to write the equation here, if this is Vs, so we can write here what? The KVL equation for it will be Vs, which is the voltage rise, minus V4, which is the voltage drop here, and this 20, which is again the voltage drop, and that would be minus V0. This must be equal to 0. Okay, so this is another equation which we are going to see here. And the third one here is the KCL. We are going to see here the KCL as well. This is the I0. So I0 is going towards this node and splitting into 2 parts, IA and IB. So here this I0 is equal to IA plus IB, and that is Kirchhoff's current law equation. So now we have 3 equations. We have this equation, let me call it A. This is equation B, let me call it here B, and this is C. Okay, these 3 equations, or let me also call it equation A prime as well. Okay, so this is the equation A prime. So now we have these 4 equations, and on the basis of them, let me calculate the values. Let us compare equation A and A prime, and from it we can very clearly see that the left hand sides of both of them are equal. So that's why IA multiplied by 20, that is equal to the IB multiplied by 80. Okay, so dividing both sides by 20, IA is equal to what? That is 4 multiplied by IB. This is another equation, let me call it 1. Okay, let me take it and put it in equation C. What will we get? Here putting it, we will get I naught is equal to the value of A is 4IB plus IB, and from it we will get the value of I naught is 5IB, and that is what we have got. Now let me take this equation B, and from it we can clearly see that Vs minus V4 is here, this 4 ohm. So applying the Ohm's law here, I into R, so I here is I naught, so I naught multiplied by 4 and minus V naught, that is equal to 0. Now let me put all these values here. So it will be Vs is 50 because the source voltage is 50 here, minus the value of I naught is 5IB, 5 into IB into 4, and the value of V naught, we can take any of these equations. Sorry, this is A. Okay, we can take any of these equations, but as here IB is involved, so let me take equation A here. So it will be minus IB into 80, and that is equal to 0. Okay, so from it let me simplify it, and simplifying it, taking it to the other side, and this one is here, so it will be 50 is equal to 20 IB plus 80 IB. Okay, so from it we can clearly see that the value of IB will be equal to 50 divided by 100, which is 0.5 amperes. Okay, so this is what, this is the value of IB. IB is known. From this value we can put it here in equation 1 and clearly see that the value of IA will be equal to, the value of A is 4 multiplied by IB, so that is 2 amperes. Okay, so this is IA. Okay, we can take IA, IB, put them here. Okay, and from this equation the value of I naught is equal to, or the generated current, which is the total current, that will be equal to 2 plus 0.5 is 2.5 amperes, and that is what, that is the value of I naught. Okay, we can take these values, put them here, either IA, either IB. Okay, so let me put them here. If putting IB here, what will we get? Putting it here, the value of V naught is equal to what? The value of IB is 0.5 multiplied by 80. So this will be what? This will be 40 volts, and that is the value of VB. Okay, so we have found some values. So let me go to the parts of it, find the value of IA. So we have already found it out. The value of IA is here. This is part A. The value of IB, that is also found out, that is here. The value of V naught, okay, we have also found it out. This is C. Okay, the power dissipated in each resistor. Okay, so to find out the power dissipated in each resistor, let me remove some parts of it here. So let me remove it. For the power dissipation, we know the formula. To find out the power dissipated in each resistor, it will be the I square into R. Okay, to find it across 4 ohm, it will be P4. Okay, it will be I naught square into 4 ohm. The value of I naught is what? That is 2.5 whole square into 4. The value of the power dissipated at 20 ohm resistor is what? That is IA whole square into 20. Let me put the value of IA, which is 2 square into 20, and the value of the power dissipated across this 80 ohm, that is the current square IB square multiplied by this 80. Okay, so it will be the value of IB is what? That is 0.5 whole square into 80. You can calculate it and then the answer of it will be here. Okay, also the power delivered by the 50 volt source. Okay, so this is the power delivered by the 50 volt source. Let me move down somehow. So part E, for the source, the value of power delivered is source current into source voltage. Okay, VI or IV, similar thing. So the current it provides is I naught, while the source voltage is 50. Okay, the current I naught, as we have found out, is 2.5 multiplied by 50. So finding it out, it will be 125 watt, and that is what? That is basically the answer of part E. If you add them all, okay, you add them all, these are the power which are dissipated in each of the resistors. You will see that the power source which is generated is equal to the power which is dissipated. Okay, so you should add them all, and all of these values will end up with 125 watt. Okay, so that's the solution of question 2.18. Today we have solved it by applying the fundamental theorems of the circuit theory. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.19, and the statement of this question is, the part A of it is, find the current I1 and I2 in the circuit in figure P2.19. So this is figure P2.19. B is find the voltage which is here. This is the voltage V0, and part C is verify that the total power developed equals the total power dissipated. Okay, so in order to do so, this is the circuit we have, and here we can see that this is the current source which is in parallel with this resistor, and here this resistor is in parallel with the series combination of these two resistors. You can see that this one and this one, the same current is flowing through them, so therefore these two are in series with each other. So therefore let me draw them. So in redrawing them, this is the current source, this is the resistor, or we can also draw the two series resistors as here it is. Okay, so this is the 100 ohm, this is 150, this is 250 ohm, this is the original current source which is of 1.5 amperes. So you can see that the current here is the I1, the current here is I2. Okay, as these two resistors are in series with each other, so therefore we can draw them like this is the source, this is the first resistor, and representing these two as the single resistor, we can add them together because in series the resistances have to be added together. So therefore 150 plus 250 is 400 ohm. Okay, this is 100 ohm, and the current source, the direction of it is here, this is 1.5 amperes. Okay, the polarity, the signs here are, this is the I1, this is I2. Okay, here we have this source current which is coming out of this, and this is I0. The value of I0 is 1.5 amperes, and the voltage V0 is here. Okay, so from this diagram we need to find out what? We need to find all the values V0, I1, I2, and all those values. So from it, by using the Kirchhoff's current law, here we can see that this is the node, this current is coming towards it, and it is now split it into I1 and I2. So therefore I0 is equal to I1 plus I2. Okay, and also we know the value of I naught, which is the source current, and that is 1.5 amperes. So therefore this I1 plus I2, that is equal to 1.5. Let me call it equation A. Now similarly, as these two, this one and this one, these two are in parallel with each other, so therefore the voltages here between these two branches will remain the same. So therefore if the voltage across it is V1 and it is V2, so let me call it V1 is equal to V2. So the value of V1, if this is the V1, it will be I1 into 100 ohm, which is of this resistor, and V2 is I2 into what, 400. Okay, or simplifying it, we will get I1 is equal to 4I2. This is equation B, and also rearranging it, we will get I1 minus 4I2. This is equation C. Sorry, this is equal to 0. Okay, so now we have A, B and C equations. Let me multiply equation A with 4 and then add A and C together. So multiplying this equation with 4, I will get 4I1 plus 4I2, that is equal to 6. Okay, and this equation is I1 minus 4I2 is equal to 0. Let me write it here as well. So this is I1 minus 4I2 is equal to 0. Let them add together. This will be cancelled out, and here we will get 5I1 is equal to 6, or the value of I1 is 6 by 5 amperes, and that is the answer for I1. Okay, let me take this value and put it into equation B. So putting it here, I will get, this is the 4I2 is equal to I1. So putting the value of I1 here is 6 by 5. Okay, so the value of I2 will be equal to, that is 6 by 4 multiplied by 5, 6 by 20, which is 3 by 10. Okay, so this is 3 by 10 amperes, and this is for I2. In this way we have solved part A of our question, in which the value of I1 is here, the value of I2 is here as well. Okay, so as these values are known, let us find the value of V0. As we can see that here, this branch, this branch, this branch, all these of threes are basically in parallel with each other. So therefore V1 is equal to V2 is equal to V0. Okay, so all these three voltages are same because all these three are in parallel with each other. So let me take any of these branches and apply the Ohm's law. So let me take this branch, okay, and let me apply the Ohm's law. This is part B. So V0 is equal to V1, and the value of V1 is I1 into 100, because of V is equal to IR. So the value of I1 is known, it is here. This is 6 by 5 into 100. So it will be here, this is 20 and 120 volts. This is the value for V0, which is the solution of part B. Similarly here, verify that the total power developed equals the total power dissipated. For it, let me move down somehow. Okay, so first of all, let me find out the power developed. So the power developed is across the source, which is here. So applying the rule here, which is P equal to IV, and here we need to find out the power which is developed. So the value of I is known, that is 1.5. okay, and the value of voltage, which is V0 here, that is also known, and we have found it out. Okay, so let me write the value 120. Multiplying with it, we will get what? It will be 180 watts. Okay, so this is 180 watts. Now in order to find the power which is absorbed, so we have three absorbing components. The first one is here, the second one is 150, this is 250. Okay, so let me find the values of the power here. Okay, so the power which is dissipated across this one, so for it we have the formula which is I square R or V square divided by R. We can use any one of them because the value of the voltage and current both are known, but as the current is already known and it is feasible for us to use the similar formula here, here and here, so let me use this one here. So I1 square into 100. Okay, so the value of I1 is 6 by 5 whole square multiplied by 100. Okay, so it will be 36 divided by 25 multiplied by 100. Okay, where did I get it from? So it is written here, so it will be 144 watts. Okay, so the value of P1 is known. Let me call it 2 P2. So the value of P2 is what? The value of P2 is I2 square into 150. Okay, and the value of P3 is here. So as these two are connected in series, so therefore I am taking them here as well as plus I2 square because the same current is flowing through both of them, so it will be 250. Okay, so let me take this one out. So I2 square multiplied by 150 plus 250. So from here we will get P2 is equal to I2 square into 400. Okay, let me move down somehow to solve it. So now P2 is the value of I2 is known, and that is 3 by 10 whole square multiplied by 400. Okay, so it will be P2 is 9 divided by 100 multiplied by 400, so ultimately we will get 36 watts. Okay, so from it we have got that the total power which is dissipated, that is P1 plus P2, so 144 plus 36, that is equal to 180 watts. Okay, so from it we have got this 180 watts, and therefore we can see that this is the power developed while this is the dissipated power, and we can see that both of them are equal in values. Okay, so what we have done today, we have solved the question 2.19, and that is what we wanted to solve today. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.20 of our book of Nilsson, and the title of the book is Electric Circuits. So the statement of the question is the current Ix in the circuit shown in figure P2.20, this is the figure, okay, is 50 milliamps. So let me write here the given data. So the current which is I of x here, this is what? This is 50 milliamps. Okay, which is what? Which is 0.05 amperes. Okay, so this is what which is given here, and also the voltage V of x is 3.5 volts. So this is V of x, and the value given for it is 3.5 volts. So V of x is how much? That is 3.5 volts. So on the basis of it, we have to find I1, which is here, V1, which is here, this one, VG, which is the source voltage, and the power supplied by the source. Okay, so this is the source, the power supplied by it. Okay, so in order to solve it, we have to keep one thing in our mind, that if we have any component, either a passive component or an active component, there are three quantities associated with it. So what are those three quantities? Those are V, I and R, okay, which are voltage, current and resistor for the linear element. Okay, so if any two of them are given, we can find out the third one very easily. Okay, so let us solve our question, and in solving it, let us first proceed with this one, and we can see that I1 is the current which flows through 200 ohm and 175 ohm as well, because these two are in series with each other. So therefore the voltage value is known, which is across it, and the resistor is also known. So we can very easily find out the value of current, because the voltage and resistors are known. So we can find out the value of I1. So from it, the part 1, which is I1, that is what? That is V divided by R by the Ohm's law, which is V equal to IR. Okay, so let me put the values here. The value of V, that is V of X, that is known, and that is 3.5 divided by R, which is how much? That is 175. Okay, so let me solve it, and after solving it, the value for it is 20 milliamps, and that is the solution of part A of my question. In part B, we need to find out the value for V1. Okay, V1 is unknown, and here we can see that if we can see this node, the current Ix is coming here and then splitting into two components, where this one is I1 and let me call this one as I2. So therefore applying KCL here, we can very easily see that I of X, which is the current coming towards this node, is equal to the I1 plus I2. Okay, or from it, the value of I2, which is flowing through this branch, through this 250 ohm resistor, that is I2 is equal to Ix minus I1. Okay, so the value of Ix is known, that is 50 milliamps, and the value of I1 is also known. So let me put them here. The value of Ix is 50 milliamps and the value of I1 is 20 milliamps. Okay, from it I can get 30 milliamps. After finding out this I2, we can see that here this is the resistor across which we have to find out the value of V1. The value of current is known, which is 30 milliamps, and the value of resistance is 250. So let me find out the value of V1, that is 250 multiplied by I2. Okay, so that would be 250 multiplied by 30 multiplied by 10 to the power minus 3 due to this one. So solving it, we will get 7.5 volts. So that is what 7.5 volts is the value of the voltage across this 250 ohm. So we have found it out, and that is the solution of part B. In part C, we have to find out the value of V of G, and here in this loop, let us use the what? Let us use here the KVL, and applying KVL here, I can very easily see that the value of Vg is equal to what? That is equal to the value across this 50 ohm resistor. So in this loop, we can see that this is V50, and V50 is the voltage drop across this 50 ohm resistor plus this V1. Okay, so plus this V1. Do we know the value of V50? No, we don't know it, but we know the value of the resistor. We know the value of the current which is given. So we can very easily find out the value of V50, that is Ix multiplied by 50 ohm. So let me put these values, that is 50 multiplied by 50 multiplied by 10 to the power minus 3. Okay, so this would be 2.5 volts. Okay, so the voltage here is given. Let me write these voltages here. So V50 is 2.5 volts. The value of V1 is 7.5 volts. So adding them together, I will get 10 volts. Okay, so that is the solution of part C. In part D, I have to find the power supplied by the voltage source. So in order to find the power supplied by the voltage source, let me solve it here. That is the power supplied by this Vg, that would be Vg multiplied by the current which is going through it, and that is I of x. Okay, so the value of Vg is known. The value of Vg is 10 and the value of I of x is 50 milliamps, so 10 to the power minus 3. So ultimately we will get what? It will be 0.5 watts what we have found out. Okay, so that is basically the solution of question 2.20. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.21 of our book Electric Circuits by Nilsson, and the statement of this question is the current IA in the circuit shown in figure P2.21, this is the figure P2.21, is 2 milliamps. Okay, this is the IA and the value of IA is 2 milliamps. Okay, so on the basis of it, we have to find what? We have to find the value of I naught. This is I naught. The value of Ig, this is Ig, and see the power delivered by the independent current source. This is the current source. We have to find the power delivered by this one. Okay, so let us start it, and in starting it, we have to find different quantities, and let me solve it here. So solution of it. Okay, so first let me have here the KCL. So according to the Kirchhoff's current law, here this current is flowing towards this node, which is here, and let me call it node A, and here the current which is flowing towards it is Ig. Okay, and then it divides into two currents. The first one here is I naught and the second one here is Ia. So according to the KCL, Ig is equal to what? That is equal to I naught plus Ia. Okay, here we just know the value of I of A. Okay, this current is known, and this is the similar current which has been flowing through all these three resistors, because these three resistors are in series. When these three resistors are in series, we have to find the equivalent resistance of that, and that would be the 1 kilo ohm resistor plus 4 kilo ohm resistor and plus 3 kilo ohm resistor. So ultimately we will get the 8 kilo ohm resistance. Okay, so this is the equivalent resistance here, and here if we can see the equivalent of it, we can see that here these two resistances, where this is the equivalent resistance, this is the 2 kilo ohm resistance, and here we have this current source. These three are in what? These three are in parallel with each other. This is the I of G, and from it this current is flowing. This is here, this one is here, and this is here. Okay, so let me have here, this is A, and let me call the voltage across it as VA. So this is the same voltage which is here and here as well. Okay, so this is the same voltage. If we can find out the value of this VA, which is here and here as well, we can find out the value of current here as well. Okay, so let me first find the value of VA, and the value of VA is what? That is this IA, which is flowing through all of these resistances. So IA multiplied by this equivalent resistance which is here, because this is I of A. Let me put these values here. The value of I is given, and that is 2 milliamps. Okay, so that is 2 into 10 power minus 3, and the equivalent resistance here is 8 kilo ohm. So that is 8 into 10 power 3. These two will cancel out, and ultimately here we will get what? The voltage here is 16 volts, and that is V of A. So let me take this one here. If this voltage is known, this is known, this is known, and this is also known, so from it we can very easily find out the value of this current, which is I naught. Okay, why? Because with each of the passive element we have three quantities associated, which are voltage, current, and resistance. If two of them are known, we can easily find out the third one. So here this resistance is known, the voltage is known, we can very easily find out the value of I naught. So using the Ohm's law, okay, the value of I naught is what? That is the value of VA divided by the resistance, that is 2 kilo ohm. Okay, so let me put these values here. So this is 16 divided by 2 kilo, so ultimately the answer of it is 8 milliamps. Okay, so the value of I naught is known, and that is 8 milliamps. Okay, so I naught is already known. So from this formula, if the value of I naught is known, the value of I is already known, so we can very easily find out the value of Ig. So the value of Ig is what? I naught is 8 milliamps, Ia is 2 milliamps, so that is 10 milliamps. Okay, so that is what? That is basically the solution of part B. Okay, so this is part B, this is part A. Okay, now we want to find out the power delivered by this source. Okay, so now for the sources we know that, let me solve it here. For the sources we know that the power which is generated or dissipated is equal to V is equal to V multiplied by I, where V is the voltage across the source and I is the current provided by it. So the voltage which is here is already VA, because all of these three are in parallel, and the current is IG. Okay, so let me put all these values. So it will be 16 multiplied by this 10, okay, into 10 power minus 3, because this is the milliamps, so it will be 160 milliwatts, and that is what? That is the solution of part C of my question. Okay, so that's it for today, in which we have seen that by employing the concepts of the series circuits, by using the KCL, by using the Ohm's law, and then applying the concept of the power generated or dissipated by the voltage or current source, we have solved this question. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.22, and the statement of this question is the current I naught in the circuit in figure P2.22 is 1 amperes. Okay, so I naught, which is this current, this is how much? This is 1 ampere. So let me write it here. The value of I naught is 1 amperes. Okay, so on the basis of it we have to find I naught, which is here. Okay, we have to find the power dissipated in each resistor. Okay, we have to find the power dissipated in each resistor, and we have to keep it in our mind that the power dissipation formula in each of the resistor here is P of R is equal to IR square multiplied by the value of the resistor. Okay, so for that we will need what? We will need the value of the current which is flowing through each of the resistor here. Okay, so let me indicate the currents which we want to find and which we had to find out. So the first one here is I naught, which is already available. The other ones are this, let me call it I4, because it is going through or passing through this 4 ohm. Similarly, let me call it I10. Okay, this current which is flowing through this one, this is I25, okay, and let me call the current which is flowing through this source, that is Ig, or the current from this source. Okay, so these are the currents which we want to find out. And what other currents we want to find out? According to the part A, I want to find out I1. Okay, similarly here I4. Okay, similarly Ig, which is here. Okay, similarly I10. These are the currents we want to find out, and this last one, that is I25, we want to find them out. Okay, so let us start and let me find them out. So first of all, we can see here that the voltage here, which is what the voltage here is 150 volts if we consider this one as the ground, and on the ground we have here the 0 volt. So the voltage here is 150, and let me call here at this point the voltage equal to VB, and the voltage here is VA. Why this? Because I want to find out the currents, and I have told you that with each of the element here we have three quantities associated. Those are voltage, current, and the resistance. If any two of them are known, the third one can be easily found out. So if the voltages are known, we can easily find out the currents here. So first of all, we can see here that the voltage here is, let me call it V50, which has been dissipated across this 50 ohm resistor. So we can very clearly see that the value of V50 is 50 multiplied by I naught. The value of I naught is known, and that is 1 ampere. So therefore the value of V50 is 50 volts. Okay, so therefore if this voltage is 50 volts, from here we can very clearly see that this is the first voltage, this is the second voltage. So we can see here that 150, which is this voltage, minus this VB, that is equal to what? That is basically the V50. Okay, as the value of V50 is known, so therefore the value of VB would be equal to what? That would be 150 minus V50. So therefore this is 150 minus 50. So ultimately the answer of it is 100 volts. So the value of VB is 100 volts, which has been known. So this value is now known. Why this? Because this is the potential difference. If we have a resistor here and we want to find out, this is VB, this is VA, and if I want to find out the voltage across this resistor, this is what this is. This VR is equal to VB minus VA, and that is what? That is the potential difference formula, and this is what I have applied here in this branch. Okay, so this is 100 volts and this is already known. So in order to find out the current here in this branch, and we can see that here this is VB and the voltage is known, so the current I25 is 100 volts, which is VB, divided by 25. So the value of it is 4 amperes. Okay, so this value is known, and that is 4 amperes. So let me write it here. This value is 4 amperes. This is known. Now here we can see that this is the current which is coming towards is, this is also the current which is coming toward this node as well. So therefore applying KCL here at VB, we can clearly see that I10 plus I naught, that is equal to the I25, which are the currents coming towards the node, is equal to the currents coming away from the node. Okay, so here the I10 is unknown, while I naught is known, which is 1. Sorry, this is plus, and also the value of I25 is 4. So therefore on the basis of it, this I10 is 3 amperes. Okay, so I10 is 3 ampere. Let me write it here as well. Okay, so these two currents are known now. Now in order to find the I4, IG and I1, I must have this VA. Okay, in order to find the value of this VA, let me move down somehow. Okay, here. So in order to find the value of this one, I can very clearly see that here applying KCL at VA, we can see that I4 is equal to I1 plus I10. Okay, the value of I10 is what? This is the current which is moving in this direction, so that therefore this is VA minus VB divided by 10. Okay, so the value of I10 is known. The value of I4 is what? That is 150 minus VA divided by 4. Okay, so let me write them here. 150 minus VA divided by this resistance, which is 4. Potential difference divided by the resistance is equal to the current. Okay, so this is the formula I have applied here. Similarly for I1, I can see that this is VA divided by 65. Okay, so that is what? I1. So VA divided by 65, which is I1, and also the value of I10, which is already known, and that is 3. Okay, once this will be solved, we will get the value of VA equal to what? VA is equal to 130 volts. So this is what we can find out from here. When you will solve this equation, this is a linear equation, only one thing is unknown, and that is this VA. When you will solve it, you will get 130. So, okay, so as from this formula, we can clearly see that the value of I1 is here, and the value of I1 is equal to VA divided by 65. So the value of VA is 130 divided by 65. So we will get 2 amperes. So the value of I1 is 2 amperes. Okay, so the value of IA is known. Similarly, from this formula, which is this KCL, we can put the value of I1, we can put the value of I10. So the value of I10 is 3, the value of I1 is 2, so 2 plus 3 is 5. So therefore here this is 5 amperes. Okay, so these currents are known. Now the value of IG, we can see that this is IG, and here to this node this I1 is coming, and this I25 is coming towards this one. So therefore let me write it here. IG is equal to the I1 plus I25. Okay, let me put their values. The value of I1 is 2, the value of I25 is 4, so this is 6 ampere. So therefore this is 6 ampere. Okay, so we can see that all the currents are known, and we have all the currents, we have found them out, and now you can apply the formula which we have already seen here, and you can find it out. From this formula you can find out all the power dissipated in all the resistors. So let me first find out it across this 4 ohm resistor, and let me use this color. So across this 4 ohm resistor I will have P4 is equal to I4 square into 4. The value of I4 is 5, so 5 square multiplied by 4, so it would be 100 watt. Okay, so P4 is 100 watt. Similarly you can find it out for this one, for this one, for this one, for this one, and all the others one by using this formula. And at the end, when you will add them together, you will see that these would be equal to the power generated by this 150 volt source, and the power generated by this 150 is equal to what? That is IG multiplied by 150. Okay, so IG is already known, that is here. You have to put this value here, multiply them with 150, and when the power dissipated by all of these resistors will be added together, it will be equal to what? It will be equal to 6 multiplied by 150, and that is 900 watts. Okay, so that's it for today. The most crucial part here was finding all the currents which are here. Let me underline them. So these are all the currents which are the most crucial part we had to do here. So that's it for today. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.23 of the book Electric Circuits by Nilsson and Riedel, and the statement of this question is: the variable resistor R in this circuit in figure P2.23, this is the figure P2.23, is adjusted until I naught equals 10 amperes. This is I naught, which is flowing through this 5 kilo ohm resistor. Find the value of R for which this current, when it is adjusted, this current is 10 milliamps. Okay, so we have to find this resistance. This is the variable resistor, and with the help of the knob or anything else, this is adjusted in such a way that the current which is flowing through this 5 kilo ohm is what? This is 10 milliamps. Okay, so the only quantity which we have now is this I naught, and the value of I naught is 10 milliamps. Okay, so if this is 10 milliamps, let us have here this voltage, let me call it V naught. So the current through this resistor is known, that is 10 milliamps, and the value of the resistance is also known. So we can very easily find out the value of V naught, that is I naught multiplied by 5 kilo ohm. So 5 kilo ohm is 5 into 10 to the power 3. So let me put these values. I naught is 10 milliamps, so 10 to 10 to the power minus 3 multiplied by 5 into 10 to the power 3. These two will cancel out, and here V naught is 50 volts. Okay, so the value of V naught is known, and that is 15 volts. Let me, okay, so this is the V naught. Apart from it, another quantities which are known are here. We have, let me call it VA. At each of the node, let me identify the voltages, and let me call it VB. Okay, this is, let me call it the ground one, and the voltage here is 0. Okay, so the value of VA, which is from this source, and we can see that this is VA minus 0 minus 80. So the value of VA is 80 volts. So the value of VA is also known, and that is 80 volts. Okay, so if this value is 80 volts, this value is known. So if we have this scenario that we have here Vx, here we have Vy, and certain voltage R, we can find out the current through it by the formula, which is I is equal to the potential difference divided by the resistor. So the potential difference here is Vx minus Vy divided by R. Okay, so let me apply the similar formula here, and in applying it, let me have this current here, let me call it I 1.5. Okay, so the value of I 1.5 is the potential difference, which is VA minus V naught divided by 1.5 kilo. So let me put these values here. So the value of VA is 80, the value of V naught is 50, and the value of the resistance in between them is 1.5 kilo. Okay, so it would be 30 divided by 1.5 kilo. So we can find it out, and it will be 20 milliamps. Okay, the value of this current is also known, and that is 20 milliamps. Okay, so this is known. Now at this junction, we can see that this current, which is 1.5, is coming towards it, and it is now splitting into two parts, which one is I naught, the other one is going through this 3 kilo ohm resistor. Let me call it I3. Okay, so by applying KCL here, okay, if I will apply KCL here, I can very easily see that, let me use this black color for it. Here I can very easily see that I 1.5 is equal to I naught plus I3. Okay, the only unknown current here is I3. So I3 can be found out by I 1.5 minus I naught. Okay, let me put these values. So I 1.5 is known, that is 20 milliamps, and I3 is I naught is also known, that is 10 milliamps. So 10 milliamps. Okay, so the value of I3 is now 10 milliamps. This current is also known. Let me underline it as well. So these currents are known. Let me remove this one. So these things are now known. Now this current is here. We can very easily find out the voltage across it. So V3K, let me have this voltage here across this one, and it would be what? It would be I3 multiplied by 3K. So I3 is known, that is 10 milliamps. So 10 into 10 power minus 3 into 3 into 10 power 3. These two will cancel out and we will get here 30 volts, which is across this one. Okay, so this is again the voltage which is known. So from it, now we know this voltage, we know the consumed voltage as well. We can very easily find out this voltage now. So from the formulation and from the potential difference formulation, we know that V naught minus VB, which is the potential applied and the potential which is remaining, that is equal to the consumed power, which is across this 3K. Okay, so from it we only don't know this VB. So VB is equal to what? That is V naught minus V3K. The value of V naught is known, that is 50. The value of V3K is also known, that is 30. So this is here. So from it the value of VB is 20 volts, which is here. Okay, so this is the 20 volts, and again this one is known. Now when this voltage is known, the potential difference is known, the resistance is known, we can very easily find out this current. Let me call it I5. Okay, by applying the formula, which is the potential difference across this resistor divided by the resistance. So applying it with here, we will get I5 is equal to the VB divided by 500. Okay, the value of VB is also known, that is 20. So 20 divided by 500, and applying it, it will be 1 over 25. So ultimately this is 40 milliamps. Okay, so the value of I5 is also known, and that is 40 milliamps. Okay, so when this one is known, what is the objective of finding it here? We need to find out the potential difference here, which is VR. We need to find out the current here, that is IR. If these two quantities are known, we can very easily find out the third quantity. So let me call here this IR. If IR is coming towards this node and this I3 is coming towards this node, these are combined together and give me this I5. So again applying at this node the KCL, what will I get here? Let me use this color. So applying KCL here, it will be I5 is equal to I3 plus IR. Okay, I5 is known. Yes, I5 is known, and that is 40 milliamps. Okay, the value of I3 is known. Yes, that is 10 milliamps. So the value of IR is I5 minus I3. Let me put these values. So I5 is 40 milliamps. Okay, and the value of I3 is 10 milliamps. Okay, so we will get 30 milliamps here, and that is the value of the current which is flowing through this resistor. This IR is known. Now in order to find the value of VR, we have two voltages across it. One is this VA, the other one is this VB, and from the potential difference formula we know that, let me use this color, we know that VR, which is the potential difference across this resistor, or that is the voltage which is consumed across this resistor, that is equal to the applied voltage minus VB, which is the remaining voltage. So VA is 80 volts, which we have found in the very start, and the value of VB, let me see that where is VB. So it is VB, so that is 20 volts. So we will get here, this is the value of the voltage across this resistor is what? That is 60 volts. Okay, so now we have this VR, we have this IR, both of them are known. I have told you that with each passive component we have three quantities relevant with each other. One is the current, the other one is voltage, and the third one is the resistance. If two of them are known, we can very easily find out the third one. So let me solve it here. Okay, let me solve it here, and by applying the Ohm's law, we can see that R is equal to VR divided by IR. Okay, the value of VR is known, that is 60. The value of IR is 30 into 10 to the power minus 3. So solving it and finding all the values, we will get it 2 kilo ohm, and that is what? That is basically the solution of our question. So what we have done, so initially in order to find out the value of this R for the current which is here, and the value of current was known, that current should be 10 milliamps, we had to find out the value of the potential difference and the value of the current which is flowing through this resistor. So for finding it out, we have found out all the voltages, all the node voltages, all the branch currents in this circuit, and ultimately we have found out the value of this resistor should be at 2 kilo ohm, so that it can provide me the value of I naught equal to 10 milliamps. So that is the solution of our question 2.23. If you have any question regarding the solution of our question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.24 of our book Electric Circuits by Nilsson, and the statement of our question is for the circuit shown in figure P2.24. So this is the figure, and here we have to find a R. Okay, so this is R, we have to find it, and after finding it out, the part B of it is the power supplied by the 250 volt source. The only source here is this voltage source, and the power supplied by it, we have to find it as well. Okay, so let us first write here the given data. So this is the 24 volts, and this current which is flowing through this 5 ohm resistor is known. When this is the source voltage, so we can see that it is connected here at these 2 points. So therefore the voltage here in these, between these 2 points, is 250 volts. So therefore if we consider this one at 0, so this one will be here, will be 240 volts. Okay, similarly in order to find out the voltage here, if this is the supplied voltage, this some voltage will be consumed here across this 5 ohm resistor, and we will get the voltage which is here. Okay, similarly this is the current, this is 4 amps current, and we can see that this 5 ohm, this 10 ohm, these two are in series, so the same current has been flowing through both of them. Okay, so let me find out the voltage here. So let me call it this VA. In order to find the voltage here, the originally applied voltage is 240 volts. So the remaining voltage which will be here would be what? It would be 240, which is the supplied one, minus the voltage which is across this 5 ohm plus the voltage which is consumed by this 10 ohm. Okay, so these are the two voltages. Let me find them. So it will be 240 minus this will be I5 multiplied by 5, which is according to the Ohm's law, and similarly here this one will be I10 multiplied by the 10 ohm, which is this resistance. Okay, we can see here very clearly that I5 is equal to the I10, and this is, as these two are in series, so therefore this is 4 amps. So let me write these values. So it will be 240 minus, let me take it out, so this 4 is here, and this 5 plus 10 is 15. So here it will be, so it is now 240 minus this is 60. So the value of VA is what? That is 180 volts. Okay, so the value here is 180 volts. So now this voltage is known, this is already known, so we can clearly see that this is the current which is flowing through this branch. If the potential difference is known, we can very clearly and easily find out this current, and let me call this current as I of x. Okay, so this I of x is VA minus 0, which is this voltage, divided by the resistances, which are 14 plus 6, so this is 20. Okay. So it will be 180 divided by 20, these two will cancel out and it will be 9 amps. Okay, so this current is the 9 amps. The current which is coming towards this one is 4 amps, this one is 9 amps, so therefore this is also the current which is coming towards this node as well. Okay, so if we apply the KCL here, let me apply the KCL and let me call this current as IY. So therefore, according to KVL, IY plus 4 ampere is equal to the IX. Okay, or the value of IY is equal to IX, which is 9 minus 4, so this IY is 5 amperes. Okay, this is the current which we know now. So at this point we know all these currents, these are known. So when we have found out this current, we can very easily calculate the potential drop here across this one. So here this is V of 4, so V4 is 4 multiplied by IY. Okay, so 4 multiplied by 5, so this is 20 volts. When this voltage is known, so this which is the applied one here can also be found out, and let me call it V of B. Okay, so let me call it VB. This is VB. So how to find it out? We can see that this VB minus VA will also be equal to the voltage which has been consumed here, and this is the original rule which we have applied here, because this is the applied one, this is the remaining one, so the consumed one will be here. So we can find it out. VB minus VA is equal to V4. Okay, let me write here all the values. So VB is equal to V4 plus VA. So V4 is how much? We have found it out, that is 20 volts. VA is how much? That is 180 volts. So this is now 200 volts. So this voltage is also known. What else do we have to find out? The potential difference across this R can be very easily found out by this one. Okay, so we have seen that this potential difference would be what? It would be 240 minus VB will be equal to VR. Let me write these values. So 240 minus VB, which is 200. Okay, so the value of VR would be here, and ultimately the value of VR would be 40 volts. Okay, so one thing is known here. The other thing which we have to find here is this I of R. Okay, so because once VR and IR would be found out, we will be easily finding out the value of R, that is VR divided by IR. We will be using this formula. These two are known, but the IR is still unknown. So therefore, if this is the current which is the applied one, or this is the same current which is going through here, if this is known, we can see that this is the 4 amps and the remaining one would be here. We can find it out as well. But here at this junction, we can see that this is the current, this one is also the current. So we have to find out these two currents. Let me call it I1. So here I1 plus IX, that is equal to IG, which is this current, but the value of I1 is still unknown. So therefore the voltage VB is known, the potential difference across this 10 ohm is also known, and the resistance is also known. So therefore the value of I1 is VB minus 0 divided by 10, which is 200 divided by 10, so that is 20 amps. Okay, taking it and putting it here, the value of Ig would be equal to, the value of I1 is 20, the value of Ix is how much, that is 9. So we can clearly find out the value of Ig, which is 29 amps. Okay, so this value is also known. So this is Ig, 4 ampere is coming towards this 5 ohm, and the remaining one will be flowing through this R. So applying KCL, we will very easily find out the current through it, and that would be the 25 amperes. Okay, so the value of IR is 25, the value of VR is how much, that is 240 minus 200, that is 40 divided by 25. So finding it out, we will get what, the value of R would be 1.6 amperes. So this is the value of the resistance which we had to find out. So the part A is solved now. Now in order to find the solution of this part B, which is the power supplied by this 240 volt source. So therefore, in order to do so, let me use this color. So here the power supplied is equal to I multiplied by V. The I which is flowing through this one is Ig. The value of it is already known, and that is 29. And the value of V is, which is the voltage source, 240. Multiplying them, we will get 6960 watts. And that is the solution of part B of our question. Okay, so that's it for today, in which we have seen the solution of question 2.24. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.25, and the statement of this question is the voltage across the 16 ohm resistor in the circuit in figure P2.25 is 80 volts. Okay, so this is the 16 ohm resistor, and the voltage given is this one, and the polarity of it is as here. So which is positive at the upper terminal, which we have described. So on the basis of this statement, what do we have to find out? The part A of it is find the power dissipated in each resistor. Okay, these are 1, 2, 3, 4, 5 resistors, and we have to find out the power dissipated in each of the resistor. Find the power supplied by the 125 volt ideal voltage source. Okay, so this is the ideal voltage source, and the power supplied by it, we have to find it out. And in last, we have to verify that the power supplied equals the total power dissipated. Okay, so that is what, that is the circuit, and we have to find out the quantities given here. Okay, first of all, we have to find out the power dissipated in each resistor, and we have to keep it in our mind that the power consumed by each of the resistor can be found out in terms of the voltage. It would be V square divided by R, or in terms of the current, it will be IR square into R. Okay, so these are the two formulas which we can use for the resistors here. But here, in order to look for it, we can do what? We can see that in order to find out these quantities, the resistances are given, which are 7 ohm, 15, 5, 30 and 16, but the values of the currents are not given. Okay, similarly the voltages are not given as well. You can use any one of these formulas and find it out, but here we are going to use this one, and therefore I will find out the value of the current through each of the resistor here. Okay, so first of all, let me redraw the circuit. This circuit is basically can be redrawn as, this is the circuit, these points are the common one in between this source and these two resistors, and here this one is the common one. Here we can see that the voltage here is 125 volt, and here let me call it 0 volts. Okay, so at one terminal of it is what, 125, the other one is 0. So therefore the total voltage here in between these 2 points is 125 volt, which is due to this voltage source. So here this is plus minus 125. Also, as this is the common point in between them, so therefore this is here, the first resistor is here Okay, the second one which is shorted here, this one is here, and the resistances which is here is connected here. Similarly, with this point we have this resistor as well. This is the 30 ohm resistor. Okay, with this point we have the 16 ohm. Okay, we can see that. Let me write their values as well. So 15, 7 ohm, 5 ohm, 30, and this one is 16, and here we can see that these two are connected. So therefore let me connect them, and these are also connected with the negative terminal of this source. Okay, so this is the circuit which we are going to solve right now. So let me choose this black color for it, and here the voltage given is this plus minus 80 volts. Okay, and the current which is flowing through this 16 ohm resistor 8, let me call it I subscript 16. Okay, similarly the current which is flowing towards this node is Ig, which is the source current. Okay, this split into two currents. The first one is the I15, which is flowing through this 15 ohm resistor, and the second one is I7, which is flowing through this 7 ohm resistor. Okay, and by going through all of this we will find out the values of IR from this circuit, and then we will apply this formula. So let us first find out this I16, because with each of the passive elements we have three quantities interrelated. The first one is the resistance, the second one is the current, the third one is the voltage. If any two of them are known, the third one can be easily found out. Okay, so with it, this resistance is known, this voltage is known, so we can clearly and easily find out this I16. So let me write here the quantities which I want to find out. So let me first write the quantities here for my own convenience. Let me use this one. So I have to find out I of G. Okay, similarly I of 7, I15. Okay, and I of 5 as well. Okay, I15, I5, then I30. Let me write it here, I30, and the last one is I16. So for I16, let me move down somehow. This is I16. Okay, so these are the currents we have to find out here. Okay, and again selecting the same black color here. Here the value of I16 is what? The value of I16 is 80 volts, which is the voltage, divided by the resistance, which is 16, and this is from the Ohm's law, which is V equal to IR, and from it we can clearly see that this is 5 amps. Okay, so I16 is where? This is here, so this is known, and that is 5 amps. Okay, now as this current is known and this voltage is also known, we can see that we have already known that the voltage here was 125 volts. Okay, so at this point the voltage is 125, so therefore this is also 125. So this voltage is 80, this is 125, so the potential difference is known here, which is 125 minus 80. Okay, as the potential difference is known, we can divide it over this 15 as well, and then dividing it we will get the value of I15. Okay, so finding it out, it will be 45 divided by 15, that is I15, and the value of it is 3 amps. Okay, so the value of I15 is 3 amps. This is already known here. So when this current is known, which is coming towards this node, and let me find out this I5, which is also coming towards this node. So these two, I15, I5, are coming towards this one, and these are combined together, and then cumulatively these are giving me I16. So let me apply the KCL here. Okay, according to the KCL, I5 plus I15, that is equal to I16, or as we want to find out this I5, so I5 is equal to I16 minus I15, The value of I16 is how much? The value of I16 is 5. The value of I15 is 3. So therefore the value of it is 2 amperes. So I5 is 2 amperes, that is here. Okay, so when this current is known, the resistance of it is already known, and we can easily find out the voltage drop across it. So that voltage is, let me call it V5, and in order to find that voltage, it will be the current, which is I5 multiplied by the resistance, which is 5. So I5 is 2, the resistance is 5, it is 10 volts. Okay, so this V5 is 10 volts. Let me call the voltage at this point V0. Okay, so the potential difference across this resistance is what? That is V0 minus the voltage here, which is 80. So now if this one is the applied voltage, this is the voltage which has been remained after the voltage which is consumed from it. So this is what? This is the consumed voltage. So therefore V0 minus 80, which is the voltage which is remaining here, this is the applied voltage, this is equal to what? This is the voltage which is consumed. Okay, so if we want to find out the value of V0, it will be V5 plus 80. The value of V5 is how much? The value of V5 is 10 plus 80, that is 90. Okay, so the value of voltage at this point is 90. Now from it we can find out the current I30 as well, because this voltage is known, that says 0 because of this voltage is known, which is 90. So potential difference divided by the resistance, it will be what? It will be I30. So potential difference is V0 minus 0 divided by 30. So V0 is 90 divided by 30. So that is 3 amps. So the value of I30 is 3 amperes. Okay, this current is also known. Now the only remaining current is this I7. Again, the potential or the voltage at this point is known, the potential at this point is known. So 125 minus V0 divided by 7 will be I7. So the value of I7 is what? Sorry, let me write it somewhere else. So let me write it here. So I7 is potential which is at the upper point, that is 125, the lower point voltage, that is 90, divided by 7. Sorry, so the value of it is 35 divided by 7, so that is 5 amperes. So the value of I7 is 5 amperes. All of these currents are known. This is the supplied voltage current which is coming towards this node, and then it is split it into I15 and I7. So let me apply the KCL here. So applying KCL, we can very easily see that Ig is equal to I7 plus I15. Let me write their values. So I7 is how much? That is 5. I15 is how much? That is 3. So that is 8 amps. So that is 8 amperes. Now all the currents which we wanted to find out are known now. Okay, so these are all the currents, and now these are the resistances, because this is the source current, and for finding the source voltage we can use the formula P equal to IV. The current of it is known, the voltage is known. So voltage is V, the current is 8, we can find it out, and 125 multiplied by 8 we will get the answer, and that is 1 kilowatt or 1000. You can multiply it and you will see that it is 1000 watt. Similarly, for this one, this is the 7 ohm resistor across which 5 amps is flowing. So to find out the power across it, let me call it P7. It will be I square into R. Okay, for it will be P15, and the current through it is 3 square into 15. For this one it will be P5, so it will be I square into R, which is 5. For it is P30. It is now 3 square into R, which is 30, and for this one let me have here P16. It will be 5 square into 16. Let me calculate them. So P7 is 5,525. So let me calculate them. It is 25 multiplied by 7, that is 175 watt across 7 ohm resistor. For P15 it is now 339 9 15 135 watts. Okay, and also this P5, this is 224 45 20 watts. P5 is 20 watts. Okay, P30 is 339 93 27, so this is 270 watts. And this one, which is P16, that is 5525 25 multiplied by 16 is 25 multiplied by 16 is 400. Okay, so that is 400 watts. So let me now add them all together. So adding them all together, this is 400 plus 270, okay, plus this one now 20, plus this is 135, plus, and this one 175. So the answer of it is 1000, which is the total power consumed or the dissipated by all these resistors. Okay, adding them all together, you have got that the dissipated power is 1000 watts. Okay, which is part A. In part B, we have also already found out the value of the applied power, and in part C we have to see that whether these two are equivalent or not. So we have verified that the supplied power is 1000 watt and the consumed power is also 1000 watts. Okay, so that's it for today, in which we have seen the solution of question 2.25. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. I hope all of you will be fine. So this is question 2.26 of our book, which is electric circuit by Nilsson, and the statement of this question is the current IA and IB in circuit in figure 2.26, which is this one, this is the figure, are 4 amperes and minus 2 amperes. Okay, so where is IA and IB? We can see here that this is IA, okay, and the value of it is 4 amperes. Okay, let me write it here. IA is 4 amperes and the value of IB, which is this current, that is minus 2 amperes. If the direction of it is here in this one, and this is what, this is minus 2A, so if the current is in the other direction like this one, if this is IB, so the only sign of it will be changed while the magnitude or the value of it will remain the same. So if I take this IB as IB prime here, so the value of IB prime is what, that is 2 amperes from the value of IB, which was minus 2 amperes. Okay, so from it we have got this IB prime. So you have got my point that if this was minus negative, so in the opposite direction the current will be of the same magnitude while the direction of it has been changed. Okay, so on the basis of it we have to find what, we have to find I of G, V of G. So this is I of G, this is V of G, and also find the power dissipated in each resistor. And I have previously told you that to find the power dissipated in each resistor here, that would be PR IR square multiplied by R. Okay, so this is one of the formula on the basis of the currents, on the basis of the voltage. That formula is VR square divided by R. So we can use any one of them, but here probably we will use this one, and for it the values of the resistors are given. What we have to find out are the currents in all of these resistors, and the part D of it is show that the power delivered by the current source is equal to the power absorbed by all the other elements. So means that this current source is the main power delivering element here. Okay. Okay, so now let us start it, and here let me first see that what are the things which are given. So first of all, let me point out some voltages and currents here. So the first, let me take this point, this point, this point. Okay, let me call this as the VA. Okay, this one as VB, and this one as VG, which is already given. It will be the ground, which is here, and the currents here, which are, let me take this current as I of B. This current taking the direction here, this is I30. Okay, this is this one, and the current which is flowing through this one, that is I5. Okay, these currents are given now. Now on the basis of our solution here, let me solve them all here. So first of all, let me find the value of V of A. As we can see that the current direction is in this way, that is IA. So therefore the polarity of it will be what? That would be plus minus here. Okay, because this is the passive element, and in passive element always the voltage will be dropped. So in voltage drop, the polarity should be like it is from positive to negative. Okay, in this way VA will be what? If we apply the KVL here in this branch from it to this one, from VA to this one, in this branch it will be what? It will be VA is equal to 100 volts because of this voltage source, and we can see that these are the same polarities which are connected. So therefore it will be V15. Okay, the voltage drop across this 15 ohm resistor. So it will be VA 100 plus V15 is IA multiplied by 15, and the value of IA is also given, that is 4. So 4 multiplied by 15, and ultimately we will get the value of it is 160 volts. Okay, so this value is the value of VA is given now. Now in order to find the value of the VB, what do we have to do? We must have all these values. Okay, so here we can see that this is VA, this is VB, this is the applied voltage, while this one is the remaining voltage, while the consumed voltage will be consumed across this 9 ohm, 11 ohm, 10 ohm. So we can apply here what? We can again apply here the KVL. Let me apply here the KVL. So here it will be VA minus VB, which is the applied, minus the remaining, is equal to what? That would be the V9 voltage drop across this one, plus the voltage drop across this 11 ohm, plus the voltage drop across this 10 ohm resistor. Okay, so let me apply them. The value of VA is known. Yes, that is 160 minus the value of VB. The value of V9 is IB prime multiplied by 9. The value of V11 is IB prime multiplied by 11, and the value of V10 is IB prime multiplied by 10. So therefore IB prime is common in between all of them, so that is IB prime, and the values of the resistors by applying the Ohm's law here. Okay, so 9 plus 11 plus 10. Okay, so it is 160 minus VB, the value of IB prime is 2, multiplied by, it is now 30. Okay, so 160 minus VB, that is equal to the 60. Okay, finding it out, the value of VB is now what? That is 160 minus 60. So that is now VB is 100 volts. Okay, so the value of VB is also known. So this one, this voltage is now 100 volts. This is now 160 volts. These voltages are known. Now when this voltage is known, this is 0, we can find out this current, which is IB. That would be the potential difference divided by the resistors. So therefore the value of IB is what? That is VB minus 0 divided by the resistances, which are 4 plus 16, 20. Okay, so the value of VB is 100 divided by 20, so that is 5 amperes. Okay, so the value of IB is 5 amperes. Now in order to find the value of I30, we can see here that there are two currents which are coming towards this junction or this point. These currents are IB prime, I30, and when these are combined together, it will give me this IB. Okay, so IB is equal to the I30 plus IB prime. Let me write their values. So the value of IB minus IB prime, that is I30. Okay, to find out the value of I30, let me write the value of IB, that is known, and that is 5 amperes, minus the value of IB prime, that is 2. So the value of I30 is 3 amperes. Okay, this current is now already known. Now this current is known, and to find out the value of this current, which is I5, what do we have to do? We must have the potential difference, which is VA minus VG. But now here, in order to find out this VG, we have this potential drop, we have this voltage. So again, applying the same formulation what we have applied here, we can write here what? We can write here VG minus VB divided by the 30, that is equal to I30. Okay, we can see that this is the potential difference divided by the resistance, that is equal to current. Now in order to find the value of the VG, it will be VG is equal to what? That is 30 multiplied by I30. Okay, and VB will be added with it, so that would be VB. Okay, so 30 multiplied by I30 is 3. Okay, plus VB, so VB is 100. Yes, so that would be the value of VG is now what? Let me calculate it. So this is 90 plus 100, that is 190 volts. Okay, so the value of VG is 190 volts. Now when this voltage is known, we need to find out the current, which is I of G. In order to find out the current here, we need to find out this current, which is I of 5. Okay, so in order to find the value of I of 5, this voltage is known, this voltage is known. So potential difference divided by the resistance, that is I5. Okay, so let me write it here. So the value of I5 is VA minus VG divided by the 5 ohm, that is VA is 160 minus 190 divided by 5, so it will be minus 30 divided by 5, so that is minus 6 amperes. The value of I5 is minus 6 amperes. So when this current is coming towards this one, it is split into two parts. One is I30, the other one is IG. So applying KCL here, let me use this point. At this point, we can see that I5 is equal to what? That is IG plus I30. Okay, the value of IG is not known while the other values are known. So therefore, the value of IG we have to find out, and that would be I5 minus I30. The value of I5 is what? That is minus 6, and the value of I30, that is already known, that is 3. So minus 3. So from it we can find out the value of IG, that is minus 9 amperes. Okay, so the value of IG is known, the value of VG is known. To find out the other power dissipated in each resistor, we have to find the currents, and these are known. This current is known, this current is known. Okay, this current is known, this is known, this is known, all these currents are known. Okay, we can see that here we have found out all these currents. So applying this formula, we can find out the currents. Okay, for the last part, it is your assignment to see that whether this is the prime source or not. For the hint, for the sources, we can find out the formulation, and that is P is equal to IV. that is what? That is the power dissipated or developed formula for the sources, which are two sources here. One is the voltage source and the other one is the current source. If you have any question, you can ask me and I will solve the part D of it as well in my next video. Okay, so that's it for today. If you guys have any question regarding the solution of this problem, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.27 of our book Electric Circuits by Nilsson, and the statement of this question is the current I1 and I2 in this circuit in figure P 2.27. so this is the figure, okay, are 21 amps and 14 amps. Okay, so this is I1, this is I2, and the values of these are given as well. So the value of I1 is, that is 21 amps, and the value of I2 is that is 14 amps. So this is the given data. On the basis of it, part A of it is find the power supplied by each voltage source. This is the 147 volts voltage source. This is again another 147 volts voltage source, and we have to find the power supplied by them. And B is show that the total power supplied equals the total power dissipated in the resistors. So in all of these resistors, we have to find out the power which is absorbed, okay, or dissipated. Okay, so these two are the power supplying sources, while these other are the resistors, which are the passive elements. In order to find the power supplied by the voltage source, what can we do here is that the formula for it is, let me write here the formula. So the formula for it is P equal to I into V. Okay, so the voltage is known, so therefore V is known, while we want to find out the current. So from it, the current here is, let me call it I naught, and from it the current, let me call it Ix. Okay, we want to find them here. So after finding them here, what we will do, the power supplied by the first 147 volts voltage source is, that would be the value of voltage source, which is 147 multiplied by the current, which is here I naught, and for the other one, that is 147 as well, this is for this one, it would be 147 multiplied by the value of the current, which is Ix here, this one. Okay, so now let me solve it, and in solving it, let me use another color. So this is also, in order to draw the voltage or the circuit here, what we have is, this is it, and this is the resistor. Okay, this is 35 ohm, this is 5 ohm, this is 10, this is the resistor, the voltage source. Okay, so it is connected here, this one is another. Okay, so these are all connected here. Let me take this one as the ground one. This is plus minus 147. Again, this is the plus minus 147. Okay, this is, sorry, this is another resistor. This is 2 ohm. Okay, 2. This is 1. This is 1. Okay, and these are here. Okay, let me call this voltage as V naught. Okay, the currents which are given here are this one and this one, and we can see here that if the voltage across this 5 ohm resistor is V5 and this is V10, okay, and the current through this 35 ohm resistor is, that is I35. Okay, and the current here, let me have this current, this is I of X, this is I naught. Okay, from it, let me write some equations. So we can see that this branch and this branch, these two are in parallel. So therefore, we can see that V naught is equal to what? That is also V35, which is across this 35 ohm resistor, and also this is the voltage drop across this 5 ohm and this 10 ohm. So therefore, it is V5 plus V10. in these resistors, we can very easily see that the value of the resistance is known, the value of current is known, so the value of the voltage can be easily found out by using the Ohm's law. So therefore V is equal to IR. So I is here what, that is I1. So I1 multiplied by 5 ohm plus the value of V10 is I2 multiplied by 10. Let me write their value. So the value of I1 is 21 multiplied by 5 plus I2 is 14 multiplied by 10. Okay, so this would be what? This would be 105 plus 140. So the value of it is 245 volts, which is V0, which is V35, and this is the value that is known. Okay, so if the value of the voltage across 35 ohm is known, we can very easily find out the value of current. So the value of I35 is what? That is V35 divided by the 35 ohm. So 245 divided by 35. Okay, let me find the value of it. Okay, so it is 245 divided by 35, that is 7. Okay, so this is the 7 amperes. The value of I35 is now known. Now here we can see that in order to find the value of I0, we can see that this is the node, the I0 is coming towards this one and then splitting into this current and this current. So therefore applying KCL here at node V0, we can see that I0 is equal to I1 plus I35. Okay, putting values here, the value of I1 is what? That is 21 plus the value of I35 is 7. So the value of I0 is 28 amperes. Okay, this value is known. Now in order to find out the value of Ix, what do we have to do? Let us first find this voltage and let me call it V0 prime. Okay, so in order to find the value of V0 prime, here in this branch we can see that the potential difference divided by the resistance is equal to what? This voltage, this current, okay, or this V0 minus V0 prime is equal to V5. Okay, this is the potential difference formula. So the voltage applied minus the voltage remaining is equal to the voltage consumed. Okay, so this V5, this is already known. In order to find out the value of V0 prime, it will be V0 minus V5 is equal to V0 prime. So now putting values here, the value of V0 is already known, that is 245. Okay, the value of V5 is, value of V5, that is here and here, this is 105. So finding it out, the value of V0 prime is 245 minus 105 is 140 volts. Okay, so this is 140 volts. This voltage is now known. Now in order to find out this Ix, we can see that this current is coming towards this junction, this current is also coming towards it, and this Ix is also coming towards it. So let me add them all together, and here it would be, according to KCL, it will be Ix plus this current, which is I2, plus this current, that is I35. This must be equal to 0. Okay, so now in order to find the value of I of x, it is minus I2 plus I35. The value of I2 is 14. The value of I35 is how much? That is 7. Okay, so it was minus 21 amperes. Okay, so the value of Ix is also known. So the two values, I0, this is I0, this is 28 amperes, this is known. So 147 multiplied by 28, and in this is 147 multiplied by the magnitude of it, because this is the voltage supplying element. So the magnitude of it is 21. Okay, so when we will calculate it, we will get the desired values. So let me find them out. Okay, so here it is 147 multiplied by 28, that is 4116 watts. Okay, and for it would be 147 multiplied by 21, it would be 3087 watts. Okay, so these are the answers of part A of our question. In order to find the solution of part B, we need to find out the currents in each of the resistors here, and then we will apply what? We will apply the formula, which is P is equal to I square into R. Okay, so the values of the resistances are known. This is known, this is known, this, all of these are known. What do we have to find out? We have to find out the currents here. Okay, so this current is already known, which is here I35. This current is known, this is known, this IX is also known, which is flowing towards it. This I0, which is flowing towards this, is known. What do we want to find out? This I2, let me call it I22, and in order to find it out, we should have this voltage. Okay, so let me call it Vx. Okay, so this is known. So now here applying KVL in this branch, okay, applying KVL here in this branch, what we will get? We will get the value of this Vx. Okay, so after we find the value of Vx, we will apply here what? This voltage is already known, that is V0 prime. Okay, so we will find it out and the current will be known. So let me solve it here as well. Okay, so let me use the KVL here. So applying KVL here, writing the equation, and we can see that the direction of the current which we had taken earlier on, this was I0, and it was from this point to this. So the actual polarity was this plus minus. Okay, so therefore applying the KVL here, we will have here this V0 from this to this point. This will be V0, and then this is the negative positive. So therefore the polarities of this V0 and this is same. So therefore it will be V1, and this one plus minus. So it is opposite than that of this. So minus 147, and then this is also opposite, and this is minus Vx. This must be equal to 0. Okay, so the value of V0 is known, that is 245. Okay, the value of V1, which is the V equal to IR, the value of I0 is known, the value of I0 is 28, and the value of R is 1. So IR is 28 multiplied by 1 minus 147, that must be equal to Vx. Okay, I have bring it here. Okay, so finding them out, what we will get, Vx is equal to, let me solve it by using the calculator. Okay, so 245 minus 147, that is 98, plus 28. So this is 126. So the value of Vx is 126 volts. Okay, so this voltage is known. Now in order to find out the current here, it will be Vx minus V0 prime, which is the voltage here, potential difference, divided by the resistance, which is 2. That was the current which is flowing through this, and that is, let me call it I22. So let me find out the value of I22. Vx is 126 minus value of V0 prime, that is, where is it? That is here. So that is 140 divided by 2. So it will be what? It will be 14 divided by 2. So that is minus 7 amperes. Okay, so all the currents are now known, And now what do we have to do? We have to put them all here, and then we will add this and this together and see that after finding the voltage drops across each resistors, then adding them, the sum will be equal to the sum of these two quantities. Okay, so that is basically the solution of part B of my question. So that's it for today. If you guys have any question regarding the solution of question 2.27, you can ask me in the comment box. See you soon. Welcome back, guys. This is question 2.32, and the statement of this question is for the circuit shown in figure P2.32. So this is the figure. Find V naught and the total power supplied in this circuit. Okay, so this is the circuit. Here we have two sources. First one here is the current source, which is the independent current source, while the other one is this diamond shaped voltage source, which is the symbol for the dependent voltage source, and upon which it depends upon I of x, because the value of it is 2I of x. This is the I of x which is flowing through this 6 ohm resistor. Okay, so let me call this voltage as V of x, and let me call the current which is flowing through this 2 ohm resistor as I1. Okay, so this is the overall condition we have in this circuit, and here we have to find this V naught and the total power supplied in this circuit. So we have two sources, this one and this one, so we have to find the powers by them and then add them together. Okay, so let me solve it, and for solving it let me choose this black color. So in solving it, okay, let me first use the Kirchhoff's current law here, and in Kirchhoff's current law we can see that this is the current which is coming towards this node and then splitting into I of x and I of 1. Okay, so therefore this 45 amperes is this current, so 45 is coming towards this node and it is splitting into I of x and I1. Okay, so let me call it equation 1. This is the equation 1. Now after it, this is the V of x, and let me have the polarity of it equal to this one. Okay, so now we have this circuit, and in this branch let me apply the KVL. Okay, applying here the KVL, let me call this one as the V of x. So 6 ohm is V of x, and then this plus minus, so therefore this is the negative voltage, so this is minus V naught, and here this voltage, this is the current is coming towards this positive and leaving this negative, so therefore this is again negative and the value of it is 2I of x. Okay, so this is what we have here. We can very clearly see that the value of V naught is what, let me call it equation 2, and here we can see that the value of V naught is 2 into I1, because I1 is the current which is flowing through this one. Okay, so that is V naught, and that is also the value of V of x is what, the value of V of x, we can see that this is through this 6 ohm resistor, so applying the Ohm's law here again, it will be 6 into I of x. Okay, in both of them I have applied the Ohm's law. Okay, so these are the two values. Okay, let me put them here, so it will be 6I of x minus V naught is 2I1 minus 2I of x. This must be equal to 0, this is equal to 0. Okay, so let me simplify it. So simplifying it, it will be 4ix, because this is ix, this is ix, minus 2I1, this is equal to 0. Okay, so now we have these two equations and two unknowns, so let me find them out. So first of all we can simplify it as well, so simplifying it we can also get 2I of x minus 2I1, this is equal to 0. Let me call it equation 3. So the first equation is Ix plus I1 equal to 45. The second equation is, sorry, this is not 2Ix minus I1, so 2ix minus I1, this is equal to 0. Okay, so let me add them together. It will be 2ix, these two will cancel out, it is equal to 45, and ultimately the value of I of x is 15 amperes. Okay, so we have found out the value of I of x. From it, let me put it here, and putting it here, what we will get here, it will be I1 is equal to 45 minus I of x, and 45 minus 15, that is 30 amperes. So the value of I1 is 30 amperes. Okay, now the value of it is here, so the V naught is 2 multiplied by I1, which is 30, so this is the value of V naught is 60 volts. Okay, so the value of V naught is known, which we wanted to find out, and the total power supplied in the circuit. So this is what, this is basically the source, and here the power developed by it is PD1 is equal to V multiplied by I, the voltage across it is V of x, and the current it has is 45, so the value of Vx is known. Okay, so that is, no, this is not known, but the value of I of x is known. Okay, the value of I of x is what, that is 15. So, okay, so the V of x is 15 multiplied by 6, so that would be 90 volts. Okay, so this is 90 volts, so 90 multiplied by 45 is the power developed by it, while for it will be the power developed by this source, it would be V multiplied by I. Okay, what is V? V is 2ix multiplied by I is I1. Okay, the value of Ix is known, yes, this is known, the value of I1 is known. Okay, this is also known here, put them here and you will get the PD2. Okay, so the total power here would be PT will be PD1 plus PD2, and that would be the solution of this part, that the total power supplied in this circuit. So that's it for today, in which we have seen the solution of question 2.32. If you guys have any questions related to the solution of this one, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.33, and the statement of this question is, for the circuit shown in figure P2.33, so this is figure P2.33, find V naught. V naught is the voltage here, which is across this 300 ohm resistor, and the total power absorbed in this circuit. So the total power absorbed in this circuit is absorbed by this 450 ohm resistor, 150 ohm resistor, and this 300 ohm resistor. Okay, so we have to find out the total power which is absorbed by all those resistors. Okay, so let us solve it, and in solving it, first of all we have to find out this V naught, and this V naught is across this 3 ohm resistor. Okay, so in order to find out the V naught here, we must have here the current which is flowing through this 300 ohm resistor. So let me call it I300 multiplied by the resistance value, which is 300. Okay, this is by Ohm's law. Okay, so according to Ohm's law, the formula is here, but we can see clearly here that the current here is flowing through this path, and this is the current which is illustrated by this diamond shaped current source, which is the dependent current source. Okay, and the value of I300 is, the value of I300 is Vx divided by 100. Okay, but what is Vx? Vx is the voltage across 150 ohm resistor. So first of all, we have to find this V of x. Okay, so let us first consider this loop, and here considering this loop, applying the KVL here, let me apply here the KVL. So here applying the KVL, let me consider this current. So if I consider this current, okay, and the value of the current here is, which is which is what I described earlier on, is, let me call I naught. Okay, so that current is I naught. So here according to the KVL here, V20, which is the voltage across this 20 volt source, is equal to the V40 plus V150. Okay, what is V150? Which is across this 150 ohm resistance, and also 450 is the voltage across this one. So let me describe them here. So this is V450, this is plus minus V150, which is described by this V of x in our question. So solving it, we can write their values are 20 is the voltage, which is V20, V450 is what? This is not known, this is unknown, but the value of current multiplied by the resistance by Ohm's law will give us the value. So that would be I naught multiplied by 450, and the value of 150 is the current multiplied by the resistance, that is again I naught, because these two are in series, so it would be 150. Okay, so taking it common here, this I naught, and then adding all together, the value of I naught will be equal to what? It will be 20 divided by 600, or it will be, this will be cancelled out, and it will be 1 by 30 amperes. Okay, so this is basically the value of I naught. From this I naught, we can very easily find out the value of this V150. So this V150 is actually V of x, okay, which is here, and this is what? This is I naught multiplied by 150. Let me put the value of I naught, that is 1 over 30 multiplied by 150. So finding it out, it is 5 volts. So the value of Vx is 5 volts. So Vx is now known. So therefore the value of I300 is Vx by 100. So it would be 5 divided by 100 amperes. Okay, or I can simplify it as well. It will be I300 is 1 over 20 amperes. Okay, this is also the solution of it. Let me take it and put it here. Okay, so putting it here, it will be V naught is equal to I300 multiplied by 300. So the value of I300 is 1 over 20, which is here, multiplied by 300. Okay, this will cancel out, also 215, so it is 15 volts. So the value of V naught is known, and that is this 15 volt. Let me use this red color for it, and this is the answer which we wanted to find out here as described by this V naught. Okay, so now this is the first solution. Now in order to find the total power here, we have to do what? Let me use this black color here. Okay, so here this is the 450 ohm resistor, this is 150 ohm, this is 300 ohm. So in order to find the total power absorbed, so the total power absorbed is what? That is the power which is absorbed by 450 ohm resistor plus the power which is absorbed by this 150 ohm resistor plus the power which is absorbed by this 300 ohm resistor. Okay, so let me call it equation A. Now here let me move down somehow. So here, in order to find the power across any resistor, we know the formula, that is IR square multiplied by the value of that resistor. Okay, so therefore now if I want to find out the value across 50 ohm resistor, I will have to have the value of the current which is flowing through this one, squaring it and multiplying by its value. Similarly, if I want to find out the value of the power across this one, it will be the current which is flowing through this one multiplied by the value of 8. And if I want to find out the value of the power across this 300 ohm, it will be the value of current flowing through this one multiplying by the value of it. Okay, so do I know the value of this I450? Yes, that is already known, and it was what? It was basically this I naught. Okay, so let me put it here, I30 whole square multiplied by 450. Okay, as the two resistors are in series, so therefore this one will also be 130 square multiplied by 150. This is 150, and the value of I 300 square, that is here, this is I 300, so it will be 120 whole square multiplied by 300. Okay, so finding the values from it and then adding it here. Okay, the first formula which is here, we will get the value which is here. Okay, you have to find them out, just calculate them and then add them all together. You will get the total power absorbed. If you had to find out the total power provided, it would be the value of the power provided by this 20 volts voltage source. So that would be the IV, so the current which is flowing through this one, that is I naught multiplied by the voltage associated with it, that is 20. The value of I naught is available, which I have already found out, that is here. The value of 20 is here, so you will get it. And also the other source is this one, so it will be Vx by 100. The current which is flowing through this one is I 300, that is already known here as well, and it would be 1 over 20 multiplied by the value of the voltage which is across this one, and that is this V naught. Okay, so that is this V naught, because both of them are in parallel. You can see that the voltage here is also the voltage across it as well, because both of these ends are connected with each other. So therefore the voltage V naught across it, this 15, so we can find them out here, and then adding them together we will get the total power which is developed in this case. So that's it for today. If you guys have any question regarding the solution of the today's question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.34, and the statement of this question is, consider the circuit shown in figure 2.34. so this is the figure. In this figure we have to find I naught. Okay, so this is I naught here, and also the part B of it is verify that the values of I naught by showing that the power generated in the circuit equals the power absorbed in the circuit. Okay, so here we have this circuit. First of all, in part A we have to find the value of I naught. This is a loop, while this one is another loop. Here we have this source which is of this diamond shaped voltage source, which is the dependent source, and it depends upon this V1 which is here across this 4 kilo ohm resistor. Okay, so let us first find the equation here, that how can we find out the value of I naught. So here applying the KVL and then finalizing the output, the output here is I naught is voltage divided by the total resistance. So the voltage, total voltage divided by the total resistance, okay, or the equivalent resistance. Here we can see that these two resistors are in series because the same current is flowing through them. So therefore in series the two resistors will be added together. So therefore 6 plus 2 is 8. So we have 8 kilo ohm, and also the voltage, the total voltage here is V1 by 2. So therefore it is V1 by 2. Okay, so this is equation number A, and here we don't know the value of V1. Okay, while this one is the V1. Now in order to find the value of V1, we can see that here the current is flowing, and the value of this current provided by this source is 10 milliamps. Okay, so therefore this V1 is basically 4 kilo ohm, and that is V1, which is the voltage across this 4 kilo ohm resistor. So therefore according to the Ohm's law, it will be I into R. The value of I is 10 milliamperes, which is 10 into 10 to the power minus 3, and the value of R is 4 kilo ohm. So 4 multiplied by 10 to the power 3, these two will cancel out, and here the value of V1 will be 40 volts. Okay, this is equation B. Now take B and put it in A. What will I get? The value of I naught will be equal to, that would be 40 divided by 2 divided by 8K. So it will be 20 divided by 8K, or it is 4 5 20 and 4 2 8, and also 2.5 milliamps. Okay, so the value of I naught is 2.5 milliamps, and we have found it out. Now in part B of my question is verify that the value of I naught by showing that the total power generated in the circuit equals the total power absorbed. Okay, so the power generated in the circuit is by this source and this source. So this is, let me call it PG, and we have to find PG1 plus PG2. Okay, this is the PG1 and this is PG2, as this is a source, and in order to find the power across any source or the power generated by any source, we have to multiply the voltage across it, multiplying it with the current which it generates. Okay, so that is P equal to IV. For this PG1 we have a current 10 milliamps. Okay, and the voltage is V1 because these two are in parallel, so therefore that is 40 multiplied by 10 milli. Okay, or it can be 10 into 10 power minus 3, so it will be 400 into 10 power minus 3, so it will be 0.4 watts. And also PG2, which is this one, it is the voltage which is V1 by 2. So V1 by 2 is 20 multiplied by the current which is I naught. So I naught is 2.5 into 10 power minus 3. Okay, let me find it out. So it will be 2.5 multiplied by 2 is 5, and multiplied by 10 is 50. 50 into 10 power minus 3. Okay, or it will be 0.05 watt. Okay, so let me add them together here. So it will be 0.4 plus 0.05, so it will be 0.45 watts, which is the power generated. Now in order to find the power consumed here, that will be the power which is consumed, that is C, that will be the power generated by consumed across 4 kilo ohm resistor plus power consumed by the 2 kilo ohm resistor plus the power consumed by the 6 kilo ohm resistor. This is 4K, this is 2K, this is 6K. Okay, now in order to find them out, as these are basically the passive elements, so therefore P will be equal to I square into R. Okay, so therefore now for 4K, if I want to find out the power for 4K, the current through it is 10 milliamps. So 10 into 10 to the power minus 3 square into 4K, so 4 into 10 to the power 3. Okay, or it will be 10 to the power minus 4 into 4 into 10 to the power 3, so it will be 0.4 watts. Okay, you can calculate it and you will see that it will be 0.4 watts. Now in order to find the value across or the power consumed by this 2K ohm resistor, so it will be 2K, and the current through it is I naught. I naught is also found out, and that is 2.5. 2.5 into 10 to the power minus 3 whole square multiplied by the 2K. So therefore 2 into 10 to the power 2 into 10 to the power 3. So here we will get 2.5 square multiplied by 10 to the power minus 3. So how much would it be? Let me find it out. So 2.5 square, this is 6.25 into 10 to the power minus 6 into 2 into 10 to the power 3. Okay, so multiplying it, it will be 6.2. Let me find it out here as well. 6.25 multiplied by 2, so this is 12.5 into 10 to the power minus 3. Okay, or finding it out again, 12.5 divided by 1000, sorry, it will be 0.0125. 0.0125. This is for the second one. Now for this third one, we have to do what? We have to use the similar one, but we have here, instead of 2 we will have here 6. Okay, so let me put here this 6. What will I get? Let me again calculate it. Okay, so here 6.25 multiplied by what? That is 6. Okay, so this is here 6, and dividing it over 1000, this is now 0.0375. so this is 0.0375. let me add all of them together. What will I get? So here it will be plus 0.0125 and this one, and plus 0.4, it will be 0.45. okay, because I have added this one and this one together, and I have got here 0.45, and that is what you can see, that the value of the power generated is equal to the power consumed, and that is what we were looking for. Okay, so that's it for today, in which we have seen the solution of question 2.34. if you guys have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.35 of our book, and the statement of it is: find A, I0, I1 and I2 in the circuit in figure P 2.35. so this is the circuit, and here we have to find this I0, I1 and I2. okay, so whatever it is given here is that this is a one loop, while these are the other loops which are on the other side of this circuit. okay, so here we can see that this is a dependent current source which depends upon this V delta. V delta is here across this 6 ohm resistor, which is in series with this 12 ohm and 18 volts voltage source. okay, so let us first find out this V delta, and this I0 is basically the current which is flowing through this loop as well. So first of all, let us have this I0 here. Let me call it this I0, and in order to find out this I0, let us apply the KVL, and according to KVL, this V18 here, let me call this one as V18. This is the voltage rise. If we take this current, this is equal to the V12 voltage across this 12 ohm resistor plus V6 the voltage across this 6 ohm resistor. okay, so the value of V18 is known, that is 18. The value of V12 is the current multiplied by the resistance according to the Ohm's law, so that is I0 multiplied by 12 plus this V6, which is the current, which is I0 multiplied by the 6 ohm resistor. okay, so that is what we have here. So according to this one, and finding out the I0 from here, this will be the 18 divided by 18, and that is 1 amperes. okay, so the value of I0 is 1 ampere. From it, let me find out V6. so V6 is basically V delta, and this V delta is 6 into I0. okay, so finding it out, we will get it 6 volts. okay, so the value of V delta is 6 volts. Similarly, here we can say that this is I0, but the direction here of this V0 is that of opposite of it, so therefore this is the opposite of this one, so therefore this is I0 here is minus 1 ampere. okay, you should keep it in your mind that the direction of this I0 and this current are in opposite direction, so therefore this one is minus 1 ampere. Similarly, now we can see that this current is V delta by 2, so therefore the value of V delta by 2 is 3 amperes, and we can see that this is the 3 amperes, the downward direction. If we consider these two are in parallel with each other, which are already in parallel, so if this is 3 amperes, the opposite of it is minus 3 amperes, because this negative sign basically demonstrates the direction of the current. So if this minus 3 is coming towards these two resistors which are in parallel with each other, so in order to find the value of I1 and I2, we can use the current divider law. Okay, so according to the current divider law, we have here what? This I1 and I2 are the currents we want to find out, and this minus 3 amperes is the current which is the source current. So now in order to find the value of I1, we need to write the total of the resistors which are connected in parallel with each other. So this is 5 plus 10 equal to 15, and if I want to find out the value of I1, I need to write the value of 5 here and multiplying with it the source current which is here. Okay, so let me find it out. It is here and it will be minus 1 ampere. The value of I1 is 1 ampere. Similarly, in order to find the value of I2 through current divider rule, we have to divide it over the same values which are the addition of the resistances of the resistors which are connected in parallel. So it is 15 because of this 10 plus 5, and with it I have to write the value of the opposite resistor in the numerator. So the opposite resistor of this I2 is this 10 ohm. So therefore this is 10 and multiplying it with the source current. Okay, I think you have got my point. So this is here 5 5 2, so this is minus 2 amperes. Okay, so this is minus 1 minus 2, and the value of I naught is also minus 1. Okay, so I hope you have got all the concepts which I wanted to demonstrate in this question. So these are basically the solutions here. This I naught, this is the solution of part A. I1 is here, this is for B, and this I2, this is for C as well. Okay, so that's it for today. If you guys have any question relevant to this question 2.35, you can ask me in the comment box. See you soon. Welcome back, guys. This is question 2.36 of our circuits book, which is by Nilsson, and the statement of this question is: for the circuit shown in figure P2.36, this is the figure P2.36. Here we have to calculate I delta. Okay, this is I delta which is flowing through this 18 ohm resistance, and V naught, this is V naught which is across this 40 ohm resistance, and B is show that the power developed equals the power absorbed. Okay, so the power developing devices here are this 50 volt independent source, this 20 I sigma dependent voltage source, this 5 I sigma dependent voltage source, and this 8 I delta dependent current source, this 20 volts independent voltage source. Okay, so these are the 5 power developing devices, while these two resistors are basically the passive elements which absorbs the power. Okay, so on the basis of it we have to find different quantities. So let me solve it, and in solving part A of our question, I delta and I naught, first of all let me choose this loop and apply here the KVL. Okay, and applying here the KVL, let me assume this current. Okay, so assuming this current, we can see that this 50 volt is rising, this is rising, and this voltage, let me call it V18, which is 18 multiplied by I delta, because of the Ohm's law, this is the voltage drop of 50 plus 20 I sigma, because I have told you that this is the voltage rise, and also the polarities of these two sources is similar, so that's why I have to add them together, and this one is plus to minus because this is the passive element, so therefore the polarity of it should be adjusted with respect to the direction of the current. So therefore the current direction is in this direction, therefore it will be plus minus. So therefore it will be V18, and V18 is V is equal to IR, I is I delta multiplied by 18. This must be equal to 0. Okay, or I can adjust it like 50 plus 20 I sigma minus 18 I delta, and let me call it equation A. Okay, also considering the current direction here, and then we can see that the polarity across this 18 ohm is already known, and this is the current. Let me call it here, and we can see that this is negative, positive, positive, negative, positive, negative. Okay, so according to this current direction, which is the clockwise, we can see that this voltage, these two are similar in polarity, while this one is the different one. So therefore let me apply the KVL here as well. It will be minus 18 I delta, okay, plus with it is 5 I sigma, and with it I have to add this voltage, which is V naught, and let me take it 40 I sigma. So it will be 40 I sigma, this is equal to 0, or writing it, I can also write it like 45 I sigma, this is equal to 18 I delta, and let me call it equation B. Okay, so from here we have seen that this is 18 I delta, this is again we have 18 I delta, and this is equal to 45 I sigma. Let me take this and put it here instead. So what I can get here, it will be 50 plus 20 I sigma, and taking it here, it will be minus 45 I sigma, this is equal to 0. Okay, let me find it out. It will be 50 minus 25 I sigma, this is equal to 0, or finding the value of I sigma from it, we will get it 2 amperes. Okay, so the value of I delta is known. Similarly, from here we can see that the value of V naught is how much? That is 40 multiplied by I sigma. So 40 multiplied by 2, that is 80 volts. Okay, so the value of V naught is known, the value of I sigma is known. Okay, now in order to find the values here, and here, we have to use the formula for the sources, which is P is equal to IV. Okay, the voltages are known and the current flowing through them are also known. We have to find them for here as well, and then add them all together. Then we have to find out the power dissipated by these two devices by the formula, which is PR is equal to IR square into R. Okay, the currents are I delta, I sigma. This voltage is already known. We have to find out this current as well, because now in this formula we know the value of I sigma as well. We have to put them here, and then PR1, PR2 will be known. We have to add them, and we will see that the power developed will be equal to the power absorbed. Okay, so that is basically the solution of question 2.36. If you guys have any question regarding the solution of it, you can ask me in the comment box. See you soon. Welcome back, guys. I hope all of you will be fine. So this is question 2.37, and the statement of this question is find V1 and Vg in the circuit shown in figure P2.37 when V naught equals 5 volts. Okay, so let me change the color of this marker, and here you can see that this is Vg, this is V naught. Okay, and also this is V1. So we want to find out V1, which is here, and this Vg. Okay, so also a hint is given here, which says start at the right end of the circuit and work backward toward Vg. Okay, so let us start from this side. Okay, and here we can see that this is the current, this is the current, and this is another current. Okay, let me call it I40, let me call it I10, and this is 40 I2. Okay, here applying the KCL, Kirchhoff's current law. okay, here at these junctions, because these three are in parallel with each other, you can see that these 3 points and these 3 points are connected to a single point. So therefore these are in parallel with each other. Okay, so now applying them here, we can see that this is current 40 I2 plus I40 plus I10. This must be equal to 0 because all of them are coming towards this common point. Okay, so here as the value of this V naught is given, okay, and according to the Ohm's law, we know that V is equal to IR. Okay, so as V is given, R is given, we can easily find out the value of current. So this is the known one from this dependent source. Okay, also this I40 is what? This voltage is known, this resistance is known. So therefore I is equal to V by R. Okay, here this is V naught by 40. So V naught is 5, which is here. So 5 divided by 40, and here we have I10, which is this current, and this voltage V naught is given. So therefore this one will be 5 divided by 10. This is equal to 0. Okay, from it we can very easily find out the value of I2, and once we found it out, the value of it is minus 15.625 milliamps. Okay, so the value of I2 is now known. Okay, once the value of I2 is known, we can see that this is the same current flowing here as well, and here this is the voltage V1 which is across all of them. So these are in parallel. Okay, here if you want to find out the value of V1, it will be I2 multiplied by 80. Okay, I know the value of I2, which is minus 15.625 milliampere. So this is 10 to the power minus 3 multiplied by 80. Okay, so finding it, we will get V1 equal to minus 1.25 volts, and this is the solution for V1. Okay, so one value V1 is known. Now in order to find out the value of VG, here we need to find out the voltage across this one, across this resistor as well, and then we will have to apply the KVL here in this loop. Okay, but in order to find out the voltages, we should have this I1, but this I1 is not known. So therefore let us apply the similar KCL here as well, and for it let me change the color as well. So for it I will use this black color. So applying the similar formulation here, we can see that this is the dependent current source. So here it is 25 I1 plus the current through it is I20. Okay, so I20 plus the current through is I80. This must be equal to 0 according to the KCL. Okay, so let me apply them and let me write their values. So the value of I20 is V1 divided by 20. So V1 is also known, that is minus 1.25 divided by 20 plus I80 is minus 1.25 divided by 80. This is equal to 0, and from it, once I1 is found out, it is 3.125 milliamperes. Okay, so now this one I1 is found out. Now using this loop here, let me call it loop A. So in this loop, in loop A, let me apply the KVL. Okay, applying KVL, we can see that VG is equal to V60 plus V260, okay, which is this resistor. Okay, so therefore in order to find the value of VG, the voltage V60 here we can find it out by using the Ohm's law. So the value of current is known here, that is I1 multiplied by 60 ohm plus I1 multiplied by 260 as well. Okay, putting the value of I1 which is here, so we can find out the value of VG, which is equal to 1 volts. Okay, so from it we can find out the value of VG, which is here as well. Okay, so that's it for today, in which we have seen the solution of question 2.37. If you guys have any question related to this one, you can ask me in the comment box. See you soon.